Welcome back to Supernova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Look up on a clear night, far from the city lights. Above you stretches an endless dark ocean sprinkled with stars. The longer you gaze, the more stars appear, as if the universe is revealing a secret tapestry. Each star is a sun, distant and powerful. Our own sun is just one among hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is one among trillions. In fact, astronomers estimate there may be 2 trillion galaxies in the observable universe. Try to imagine that. 2 trillion island universes, each brimming with stars beyond counting. If you could snap your fingers and count one galaxy per second, you'd be counting for over 65,000 years just to list them all. Within those galaxies are countless worlds. Some scientists say as many as 6 billion Earth-like planets may orbit stars in our Milky Way alone, and perhaps 12 quintillion across the cosmos. 12 quintillion Earths, 12 quintillion possibilities. The scale of space truly defies comprehension. It's a void, a vastness, but also a canvas of nearly infinite possibilities. Floating on a tiny rock called Earth, we humans have always felt small under this sky. Tiny, yet special, because we can ponder it. We can ask, what is all this? What is the nature of space, of reality? How amazing that the universe is comprehensible enough that we can study it, yet mysterious enough to inspire wonder. As the famous astronomer Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We are made of atoms forged in long, dead stars, now come alive to gaze back at the sky. Through us, the universe questions its own existence. And one of the most profound questions we can ask is, are we even real? Could all this enormity, this grand cosmos, be an elaborate illusion or construction? Could we, our lives, our planet, our universe, be part of a grand cosmic simulation? That question sounds like science fiction, yet it has leapt from the pages of novels and movie scripts into serious scientific and philosophical debate. What if our reality is not the base reality? What if it's a program, running on some unfathomably complex computer, created by entities beyond our realm of existence? It's an idea that can feel both thrilling and unsettling, the simulation hypothesis. In essence, this hypothesis suggests that what we perceive as the physical universe, including space and time, might be an artificial simulation, like a high-resolution virtual reality designed by an advanced intelligence. In other words, maybe we are living in someone else's computer program. Pause for a moment and really consider that. The ground beneath your feet, the air you're breathing, the light from those distant stars, could all of it be code? If it were true, if everything we know is part of a simulation, how would we know? Would it even matter to us inside it? And who, or what, might be the programmer of the cosmos? These questions take us to the edge of what science can speculate and what philosophy can ponder. They force us to confront the nature of reality from a perspective that is both deeply cosmic and intensely personal. Tonight, we'll embark on a journey through this maze of ideas. We'll wander the vastness of space, marveling at its wonders, and we'll delve into the simulation hypothesis, examining why some prominent thinkers believe it might be true and why others remain skeptical. We'll touch on ancient philosophical puzzles and cutting-edge scientific experiments. We'll meet the scientists and philosophers wrestling with these questions, from those studying the quantum underpinnings of reality, to technologists pushing the boundaries of virtual reality, to philosophers questioning whether real and simulated are even meaningful distinctions. Along the way, we'll peer into the very code of the universe and see if there are hints that reality has a designer, and we'll imagine what it would mean for our lives, our purpose, our future, if we are indeed characters inside a grand cosmic simulation. This idea, questioning the reality of reality, is not entirely new. Long before computers and simulations, humans sensed that the world might not be exactly as it appears. Over 2,000 years ago, the Greek philosopher Plato proposed a famous allegory. Imagine people who have lived chained in a dark cave all their lives, Plato said, facing a blank wall. All they ever see are shadows cast on that wall, shadows of objects behind them, objects lit by a fire. Those shadows are their entire reality. They give them names. They think they're real things, but they're just projections, mere silhouettes of something truer. One day, a prisoner is freed and stumbles outside into the dazzling sunlight. For the first time, he sees the full, rich world beyond the cave and realizes the shadows were just a pale imitation of reality. Plato used this allegory of the cave to discuss knowledge and enlightenment, but it resonates eerily with the simulation idea. If we are like those cave prisoners, then our day-to-day world might be the shadow play, while the true reality exists outside our current perception. Could it be that we are living in a cave of sorts, seeing shadows and mistaking them for the whole of existence? Across cultures, similar notions appear. In ancient Chinese philosophy, Zhuangzhou wrote of a vivid dream in which he was a butterfly fluttering about. In the dream, he was happy, unaware of any other life. When he awoke, he found himself lying in bed as a man, but then he wondered, was he a man who had dreamed he was a butterfly, or a butterfly now dreaming he was a man? This butterfly dream story captures a deep puzzle. How can we know if our experience right now is real, or some kind of dream or illusion? Likewise, in Hindu philosophy, the concept of Maya describes the world as an illusion, a sort of cosmic play. And the French philosopher René Descartes, in the 17th century, famously imagined an evil demon that could be tricking him with an illusory world, an early pondering of a virtual reality created to deceive the senses. Descartes realized the only thing he couldn't doubt was his own mind's existence, which is not so far from the simulation question. If everything were simulated, the one thing we might be sure is real is our own consciousness experiencing it. We humans have a long history of questioning reality, but the simulation hypothesis, as we discuss it today, took these age-old questions and reframed them in the context of modern technology and cosmology. It's as if the ancient philosophical doubts met the era of computers and video games and found a new form. A key moment in popular culture was the release of The Matrix in 1999, a film that riveted audiences with its depiction of humans unknowingly trapped in a perfectly simulated world. People plugged into a virtual reality, living in a shared illusion while their bodies lay elsewhere, asleep. The Matrix wasn't the first story of its kind, but it presented the idea so powerfully that it became a cultural touchstone for this concept. Suddenly, the question, what if we're in a simulation, moved from esoteric philosophy to everyday conversations. After watching Neo choose between the red pill and blue pill, a whole generation had a reference point for discussing the nature of reality. Just a few years after that film, in 2003, a philosopher named Nick Bostrom at Oxford University gave the simulation idea a rigorous academic form. Bostrom wrote a paper with a title that cuts straight to the core: Are you living in a computer simulation? In it, he proposed a sort of logical argument, a trilemma. It goes something like this. 1. Almost all civilizations at our stage of technological development go extinct before they ever become technologically posthuman. In other words, maybe it's incredibly rare to survive long enough to create the kind of computing power needed for world-sized simulations. 2. If a civilization does reach that advanced stage, perhaps almost none of them would be interested in running simulations of minds like their ancestors. Maybe it's simply not done. whether for ethical reasons or lack of interest. 3. If the first two propositions are wrong, then the number of simulated conscious beings would far, far exceed the number of original beings. And if that's the case, the odds are that we ourselves are among the simulated minds, not the original biological ones. Bostrom argued that at least one of those three must be true. Either we're doomed to never reach that advanced stage, or we'll reach it, but never simulate worlds with conscious beings, or we're almost certainly in a simulation right now. Importantly, if you think there's any significant chance that advanced civilizations would run such simulations, then you have to admit the possibility that we might be in one. To put it another way, unless we go extinct or never bother to use our future computers this way, it's quite likely that reality as we know it is a digital illusion. That's the unsettling logic Bostrom presented. He even concluded, somewhat playfully yet provocatively, that the belief that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. In simple terms, we can't have it both ways. We can't both expect our descendants to create loads of simulated worlds and also assume we're in the one real world. If creating simulated universes becomes possible and common, then statistically, our own reality is probably one of the many simulations rather than the one original. This argument hit the scholarly world like a jolt. It was a serious professor, not a Hollywood director, suggesting this mind-bending scenario in earnest. And it came at a time when computing power was growing exponentially, and our own simulations, think computer games, virtual reality experiments, AI programs, were becoming more impressive every year. Bostrom's paper gave a sort of credibility to an idea that, until then, was mostly science fiction. It moved the conversation into journals and conferences. People began to debate, not just, could this be true, but what evidence would there be, and how would this change things? It didn't stay in academia. The idea spilled out into tech companies, into late-night dorm room discussions, into Reddit forums and YouTube channels. Even major public figures started taking it seriously. Perhaps the most famous among them is entrepreneur Elon Musk, known for his ventures in electric cars and space travel. Musk has repeatedly talked about the simulation hypothesis. In 2016, speaking at a conference, he put it in his characteristically blunt terms. There's a 1,000,000,000 chance we're living in base reality, meaning he thinks the odds that our reality is the original reality are almost zero. In other words, Elon Musk believes it's extremely likely that we are living in some kind of computer simulation. That statement grabbed headlines around the world. Here was one of the most high-profile innovators on the planet, casually asserting that everything we experience might be artificial. Musk's rationale was simple. Look at the trajectory of video games. In the 1970s, we had Pong, 2 rectangles and a dot. Today, we have hyper-realistic 3D simulations with millions of players in richly rendered worlds and virtual reality technology that can trick our senses for a time. Given another few decades or centuries, the argument goes, it's inevitable that our technology will produce simulations indistinguishable from reality. If we have that potential, then perhaps some other civilization in the universe already achieved it. And if even one civilization did, the number of simulated universes could be astronomically large. So from Musk's perspective, the math makes it hard to believe we are the one lucky draw that is actually real. He's not alone. Astrophysicist Neil deGrasse Tyson, a science communicator who hosts TV shows and podcasts, has said he thinks there's a very high chance the universe is a simulation. At a debate in 2016, Tyson suggested the likelihood might be better than 50-50 that we live in a simulation. Philosophers like David Chalmers and physicists like Max Tegmark have also entertained the idea in public discussions. Suddenly, the simulation hypothesis has moved from a fringe idea to a topic discussed by scientists at prestigious forums. In fact, the American Museum of Natural History held an entire panel debate on it, with experts from different fields. One journalist described that debate, noting that philosophers, physicists, technologists, and, yes, comedians are all grappling with the idea. It has, in a sense, become mainstream speculative thought. But let's step back a moment. Is there any evidence for this idea, or is it all circumstantial and philosophical? Why would serious people even consider that we might detect the telltale signs of a simulation? To explore that, we need to delve into the nature of physical reality itself, into space, time, and the quantum realm, and see if our universe behaves the way we'd expect a base reality to behave, or if it has quirks more suggestive of a programmed environment. First, consider the nature of space. We usually think of space as simply emptiness. You might picture the void between stars as a silent, cold nothingness. But in physics, space is not truly empty. It has properties. It can bend, ripple, and even boil, with tiny particles popping in and out of existence. According to Einstein's theory of general relativity, space is like a fabric that can stretch and curve. Massive objects like stars and black holes warp this fabric, which is what we feel as gravity. Space, in this view, is dynamic. It's not just an empty stage where things happen, it's part of the actors. When we observed gravitational waves from colliding black holes for the first time in 2015, it was literally space itself trembling, like a pond rippling when a stone is dropped. This is a far cry from the simple nothingness one might assume space to be. Now, zoom down to the tiniest scales, and space gets even weirder. In quantum mechanics, even what we call a vacuum seethes with activity. Particles and antiparticles can spontaneously appear in pairs, exist for a fleeting moment, and annihilate each other. A phenomenon allowed by the quantum rules, as long as it's brief. This isn't science fiction. It's been experimentally observed. If you think about it, this is almost like the universe has a constant background computation running, even when nothing is there. It's as if the simulation never truly idles. There's always some processing happening in the vacuum of space, a constant quantum hum. What about the size of space? The observable universe, the part of the cosmos we can in principle see, extends about 46 billion light-years in every direction from us. We often say 13.8 billion years old, but due to expansion, the radius is larger in light-years, and that's just what's observable. Space could be much larger, potentially infinite. If a simulation were to recreate such a vast space in full detail everywhere, the amount of information would be mind-boggling. Could any computer, even one built by gods or advanced aliens, simulate 2 trillion galaxies worth of stars, planets, and particles? It seems intractable. But if we were inside a simulation, there might be ways to cheat and not simulate everything at once. Think of how video games work. When you're playing a game, the computer or console isn't rendering the entire game world at high resolution all the time. It's only rendering what the player is currently seeing or experiencing. Turn away from a scene, and the game might stop calculating it until you turn back. Some have suggested that a universe simulation might do something similar, only calculate details as needed. This ties into one interpretation of quantum physics that's frequently mentioned in the context of simulations: the idea that observation seems to play a role in how quantum events resolve. There's a famous experiment, the double slit experiment, where particles are fired at a screen with 2 narrow slits. If you don't observe which slit a particle goes through, the particle acts like a wave of possibilities, going through both slits and creating an interference pattern on a detector screen, as if it interfered with itself. But if you set up a detector to watch the slits, the interference pattern disappears. The particle behaves like a single, well-defined object that went through one slit or the other. Simplifying a lot, the outcome changes depending on whether it's observed. To many, this suggests that reality decides on an outcome only when it has to. when an observation is made. This is a cornerstone of quantum mechanics, often summed up as the observer effect. Now, some physicists will caution that it's not that consciousness causes the change per se, just the interaction with a measuring device. But the philosophical interpretation lingers. Perhaps things aren't determinate until they need to be. If you were designing a simulation, that's actually a smart way to save resources. Don't calculate something until someone tries to look at it. In a way, the universe already behaves like that at the quantum level. It's as if there's a level of reality that's in potential form, a haze of probability, and it becomes concrete only upon interaction. Could that be the sign of a rendering engine at work? As Tyson and his comedian colleague Chuck Nice quipped on Star Talk, maybe that's why we have the speed of light limit in our universe. Perhaps the simulation doesn't allow anything to travel faster than light, because then you could get to another star or galaxy faster than the program could load the details. In their playful exchange, Chuck Nice suggested, maybe that's why we can't travel faster than the speed of light, because if we could, we'd be able to get to another galaxy before they can program it. And Tyson added with a laugh, so the programmer put in that limit. It's a joke, but it perfectly illustrates how a computational constraint could manifest as a law of physics. Our cosmic speed limit might be akin to the draw, distance in a video game, preventing us from moving too fast for the simulation to keep up. Let's think about other hints. Some scientists have looked for signatures of discretization in space, essentially evidence that space is not continuous, but made of tiny pixels or chunks, like a digital grid. If the world is simulated, it might be running on a lattice or grid at the smallest scale. In our current physics, we have the concept of the Planck length, which is far smaller than anything we can directly measure. It's often thought of as a scale at which classical ideas of space break down and quantum gravity might take over. If space were truly pixelated, the Planck length might be the size of the pixels. A few researchers have proposed experiments to detect this. Dr. Zohreh Davoudi, a physicist at the University of Maryland, has discussed how, if space-time is discrete, there could be slight changes in how high-energy particles travel across cosmological distances. For instance, we might detect a tiny preferred direction or an upper limit in the energy of cosmic rays because of the underlying grid. Imagine if you tried to draw a perfectly straight, extremely long line on a pixelated screen. At some point, the discreteness might show anomalies. Davoudi specifically noted that if space-time is on a lattice for the simulation's sake, extremely energetic particles might not behave exactly as expected in a smooth continuum, possibly revealing a break in a symmetry-like rotation. So far, no such anisotropy in cosmic rays has been observed. If one were, it would be intriguing, though not absolute proof of a simulation. But the fact that physicists are even contemplating such tests shows how seriously the idea is being taken. Another striking piece of maybe evidence came from James Gates, a theoretical physicist known for his work in supersymmetry. Gates found something unexpected in the equations he was studying. Deep in the mathematical framework of certain supersymmetric models, he discovered equations that are identical to those used in computer error correcting codes. Error-correcting codes are algorithms programmers use to ensure data isn't corrupted. Basically, they help systems self-correct mistakes. They are, as Gates put it, what make browsers work, allowing digital information to transmit reliably. So, it was quite startling to find them knitted into the fundamental equations describing how particles and forces might work. Gates said, "I no longer can say that people like Max Tegmark are crazy." Upon realizing this, implying that seeing something so digital, looking in the bedrock of physical law gave him pause. He mused that finding such code in nature's equations, if nature weren't a simulation, would be an extremely unlikely coincidence. Does that mean the universe is a computer program? Not necessarily. It could be that our mathematics just happens to take that form, or perhaps there's a deeper reason for those codes that has nothing to do with actual computing. But it's tantalizing details like this that make scientists raise an eyebrow. It's as if you were walking through a forest and found a computer chip lying on the ground. You'd wonder, is there an intelligence at play here, or is it just an odd-shaped rock that happens to look like a chip? Cosmologist Max Tegmark, whom Gates referenced, has pushed an even broader idea, that the universe fundamentally is mathematical. Tegmark often points out that the more we study nature, whether it's the motion of planets or the behavior of subatomic particles, we find that mathematics describes it with uncanny precision. The laws of physics can be written in equations. They have symmetry and structure, much like a code. Tegmark's perspective is that perhaps the universe isn't just described by math, it is math in a very real sense. If one were a character in a video game, he notes, at some point you might notice the strict mathematical rules of your world and suspect there's an underlying code. Our scientists, by uncovering equations, might just be reading bits of the cosmic source code. This doesn't prove a programmer in the usual sense. Tegmark is careful to frame it as the universe being a mathematical structure on its own, but it certainly rhymes with the simulation narrative. After all, what is code, if not mathematics, implemented in a machine? So from the quantum behavior suggesting on-demand rendering, to potential spatial pixels at Planck scales, to literal error, correcting codes popping up in theoretical physics, the universe has some hints that tickle the mind. None of these are smoking guns. For every intriguing clue, skeptics can offer alternative explanations, but they add up to a picture of a universe that is surprisingly information-like. The physicist John Wheeler once coined the phrase "it from bit," meaning that at a fundamental level, everything may arise from binary choices, from information bits. More and more, our best theories of physics speak in terms of information. Black holes, for example, are often described by how they store information on their event horizons. Quantum entanglement is being investigated as the possible pixel glue of space-time itself in some modern theories. Scientists are exploring the idea that space-time geometry might emerge from patterns of entanglement, essentially from information networks. It's almost as if the universe behaves like a giant information processor. And if so, one can't help but ask, who or what is processing that information? Is it just the universe being the universe? Or is it a computer built by something beyond it? Now, let's take a step further out and look at a completely different line of thinking, the Fermi paradox and the eerie silence of the cosmos. In our opening, we talked about the vastness of space and the countless planets that likely exist. Given those numbers, many scientists believe that life, and eventually intelligent life, should have arisen in many places across the cosmos. Even if a fraction of those 12 quintillion Earth-like planets developed life, and a fraction of those developed intelligent civilizations, there ought to be many alien civilizations out there, some perhaps far older and more advanced than us. This reasoning is encapsulated in the Drake equation, which is a probabilistic formula to estimate the number of communicative civilizations in our galaxy. Depending on what numbers you plug in, you might predict anything from 0 to thousands of civilizations. But many reasonable estimates suggest the galaxy should be home to several at least, and the universe at large, many more. So physicist Enrico Fermi famously asked, "Where is everybody? If life is common, why haven't we seen any evidence? No confirmed signals, no spacecraft, no alien visitations that withstand scientific scrutiny. The skies are quiet and have been for as long as we've been listening." This puzzlement is what we call the Fermi paradox. Over the years, people have suggested numerous possible solutions. Maybe life is rare, or intelligent life destroys itself quickly, or maybe alien civilizations are out there but choose to hide or observe us from afar. One particularly mind-bending proposal is directly relevant to our topic. Perhaps we don't see aliens because the universe has been designed to appear empty to us. This is sometimes called the planetarium hypothesis. Imagine we are inside a giant virtual planetarium or terrarium, crafted to give us an illusion that we are alone. In 2001, science fiction author Stephen Baxter wrote an essay suggesting exactly this: that maybe advanced extraterrestrials, perhaps ones who reached a Type 3 civilization on the Kardashev scale, have created a simulation around us so that we perceive a vast, empty universe. They keep us in the cosmic equivalent of a snow globe. We look out and see stars and galaxies, but maybe the details beyond a certain point are all a projected illusion. Baxter wrote that our universe could be a form of virtual reality planetarium designed to give us the illusion that the universe is empty. In this scenario, the reason for the simulation is key. It might be to quarantine us or protect us. Perhaps they worry that if we knew about them, or if we encountered them, it would disrupt our natural development, or cause us to panic. Or maybe it's to protect themselves, ensuring we can't locate them. It's a wild idea, but it does answer Fermi's question in a creative way. We haven't seen aliens because our reality is constructed so that we won't. Whenever we point our telescopes out and listen for signals, the simulation dutifully returns a result of grand silence because that's its programming. If true, it implies our simulators are not necessarily our descendants, but could be alien beings in a higher level reality. They might be running a simulation of the universe and intentionally omitting themselves. It's like we're NPCs in a video game who aren't allowed to meet the game masters. Of course, if that's the case, what happens if one day we humans start reaching out into space in earnest? Baxter mused that maybe the simulation has built in limits to stop us. For example, the laws of physics that limit space travel could be intentional. The enormous cosmic distances and the finite speed of light act as barriers to keep us from ever leaving our sandbox region of the simulation. If somehow we got close to escaping, say we built ships that approach light speed, perhaps the simulators would intervene with some new obstacle. It's a bit like the Truman Show, where the main character tries to sail away from the island and literally bumps into the sky, which is a painted dome. Is our sky, our space, a painted dome in some sense? Hard to believe, and currently impossible to know. But it certainly fires the imagination. Now, before we get carried away, it's important to note that while some researchers find such ideas intriguing, they also acknowledge limitations and criticisms. For instance, can a simulation even be that large and perfect? One challenge is what we call computational complexity. If you were to simulate an entire universe down to the level of atoms or quarks, the amount of computing power seems unfathomable. We struggle to simulate even a tiny chunk of the physical world with our best supercomputers. Simulating the quantum behavior of a few dozen particles can tax our largest machines. In fact, researchers using quantum Monte Carlo simulations find that the complexity grows exponentially with the number of particles. They've pointed out that to simulate just a small piece of reality at full quantum detail might be effectively impossible for any practical computer, even one the size of a planet or a star. So skeptics argue, how could a simulator handle 10 Bow 80 particles, each doing their quantum dance? Well, proponents of the simulation idea respond that a simulator could use shortcuts. We already touched on one. Only simulate what's needed. Perhaps the simulating computer doesn't bother to calculate the interior of distant stars or the exact behavior of every galaxy unless it becomes relevant to the story. Perhaps it focuses on Earth and its vicinity, and everything else is painted in broad strokes, with detail filling in only when we look closely. Some have even speculated that things like quantum indeterminacy or chaos theory could be features that prevent us from ever predicting and thus compressing the universe's behavior. If the simulators are clever, they might not need infinite power, just very sophisticated algorithms that always stay a step ahead of the players. Another counterargument is Occam's razor. This is the idea that, all else being equal, the simplest explanation that fits the data is preferred. The simulation hypothesis is, to put it mildly, not the simplest explanation. It posits an entire additional layer of reality, with beings and technologies far beyond our own, all to explain a universe that we could otherwise just take as is. Physicist David Kipping performed a Bayesian analysis and initially found about a 50% odds for us being in a simulation, given no prior information. And he noted that if humanity ever creates simulations of conscious beings, those odds would dramatically tip toward the simulation scenario. But Kipping himself has said that because the simulation idea is so elaborate, Occam's razor might count against it. Without evidence, why assume a complicated multi-layer reality when a single-layer reality works fine? He and others have likened it to a philosophical speculation that may not be testable, and if it's not testable, can it be considered scientific? After all, any evidence we find could be just features of the universe, not proof of external programming. The ultimate problem is falsifiability. We can't currently devise an experiment that would definitively tell us, yes, this is a simulation, or no, it's not. If the simulation is perfect, any result is just part of the simulation. As philosopher David Chalmers put it, there's certainly not going to be conclusive experimental proof that we're not in a simulation. Any evidence we could ever get would be simulated. In other words, a clever simulator could always tweak things to keep us guessing. So some argue, what's the point of even debating it if we can't prove or disprove it? Perhaps, they say, we should just proceed as though the universe is real. Lisa Randall, a prominent physicist, has expressed that she finds the simulation hypothesis pretty implausible and not very useful. We might as well keep doing science and not worry about being in a simulation. She remarked, "We don't know the answer, and we just keep doing science until it fails." If at some point our scientific understanding truly hits a wall that can only be explained by, "we're in a sim," then maybe we'll reconsider. But until then, the hypothesis is more of a fun thought experiment than a practical guide. Randall also noted that thinking about such scenarios can still be valuable if it motivates us to ask interesting questions about physics we can test. In a sense, even if we don't buy the simulation theory wholesale, exploring it might spark new ideas or new ways to look at the cosmos, and that is certainly worthwhile. Now, let's imagine for a moment, what if we did discover evidence we're in a simulation? Or suppose one day an anomaly happens that simply can't be brushed aside. Maybe a message appears in the sky that can't possibly be natural, or we find an actual glitch in physics that is so specific it points to design. How would we react? Would it change how we live our lives? There are many science fiction scenarios about this. One could imagine society reacting with denial, or with a religious fervor, or maybe with panic, or conversely with relief. That explains everything. It's hard to know. Some thinkers have said it shouldn't change much on a day-to-day level. If you find out the universe is a simulation, the tree in your backyard is still a tree. The love you have for your family is still real to you. The taste of your favorite food is the same. You still have to go to work, avoid stepping in front of buses and all that. In fact, in a perfectly run simulation, you can't actually do anything outside the rules of the simulation, so you'd have to continue living by its laws. But psychologically, it could be a heavy realization. Would people feel less guilty about doing wrong, thinking, none of this is real, so what does it matter? Or would they feel more purpose, like, we're part of a planned creation, we better make our creators proud? Different individuals might react differently. Interestingly, the simulation hypothesis has a way of merging with traditional ideas of spirituality and religion. If there are creators outside our reality who made our world, how is that so different from concepts of God or gods? Some have pointed out that the simulation argument is like a technologically updated creation story. Instead of a supernatural deity, you have a super intelligent programmer. Instead of mystic heaven, you have another universe that hosts the computer. It reframes phenomena like an afterlife. As Dr. James Gates noted in that panel, if we are in a simulation, reincarnation might be literally possible. Our lives could be restarted or the program run again, effectively bringing everyone back to life. If you've ever played a video game, you know that dead characters can often respawn, or a saved game can be loaded to replay a scenario. In a simulation, maybe death isn't permanent, The data of your mind could be saved or copied. The simulation could also allow for things that look like miracles. Perhaps the simulators can intervene or tweak things now and then, which might appear to us as divine acts or anomalies. It's a whimsical parallel, but it does start to blur the line between science fiction and theology. In fact, Gates said that the simulation idea starts to break down a funny barrier between what people often think is the conflict between science and faith. Because here we have a scenario with creators, possibly an intention or purpose, and potentially even a form of life after death. Yet it's framed in a logically and technologically grounded way, rather than a mystical one. It's almost like a bridge between two worldviews. Of course, not everyone would agree with venerating simulator beings as gods. Philosopher Chalmers quipped that even if we were in a simulation controlled by higher beings, he'd refuse to worship the simulators. After all, they might be just scientists or gamers, not morally superior divinities. And if they allowed suffering in the simulation, one might question their ethics just as we question why a benevolent God would allow evil. Are we just an experiment? Entertainment? Education? Who knows what their motive would be? There's even a theory that maybe it's us, our future descendants, running ancestor simulations to study their own history, which raises all sorts of paradoxes and moral questions about creating conscious beings for study. Bostrom himself pondered on whether it would be ethical to run simulations of suffering. Let's entertain a positive angle. If we are in a simulation, maybe the simulators are benevolent. Perhaps we're a kind of long-term art project, being carefully tended. If at some point we're in danger, maybe they'd subtly steer things to save the project. Some people have humorously suggested that the lack of catastrophic asteroid impacts in recent times, or the fortuitous timing of certain events in humanity's past, could indicate someone wants us to reach a certain stage. That's highly speculative and arguably just human-centric storytelling. But it's true that the simulation idea can either make you feel extremely small or strangely important. Another fascinating speculation: what if we ourselves create simulations within this universe? If we build our own simulated realities, populated by AI beings who think they're alive, then we'd have a nested simulation. Perhaps that's already happened. Maybe the simulators who built our world are themselves simulated by a higher level, and so on. This could lead to a chain of simulations within simulations. Tegmark pointed out a philosophical issue with Bostrom's argument. What stops an infinite regress of simulated worlds? If simulations become common, there could be many layers. But could it be simulations all the way down? At some point, there might need to be a base reality where the first simulation runs. If we're deep in a stack of simulations, our chances of reaching or understanding the true base reality are extremely slim. It would be like a character in a video game becoming aware of the game and then trying to figure out the world of the game developers by only exploring inside the game. They might get some hints, but can't break out of their level. Some tech visionaries have even talked about trying to break out of the simulation. There were reports that certain billionaires in Silicon Valley were funding research to find a way to detect or escape the simulation. It sounds like the plot of a movie. The rich and brilliant trying to crack open the sky of the Truman Show. While those specific stories might be exaggerated, it's true that the simulation hypothesis has captivated some of the most future-oriented minds. If you truly believed we're in a simulation, one radical idea would be to attempt to communicate with the creators. Maybe not by building a physical Tower of Babel, but perhaps by sending a clever message or creating a scenario within the simulation that stands out. Some have facetiously suggested that we should perform bold, unpredictable actions so as to get the simulator's attention. Max Tegmark, at the end of that debate, half-jokingly advised, "If you're not sure whether you're actually simulated or not, my advice to you is to go out there and live really interesting lives and do unexpected things so the simulators don't get bored and shut you down." That might be the best advice regardless of simulation status. Live an interesting, meaningful life, just in case someone is watching from above, and for your own sake if no one is. Now, we've journeyed through a lot, from the starry expanse of space to the subatomic quirks of quantum physics, from ancient philosophy to cutting-edge computational theory, from the loneliness of the cosmos to the possibility that we're not alone at all, but rather surrounded by an invisible infrastructure of a simulation. Through it all, one thing is clear: the line between reality and illusion is delicate. Whether or not we live in a simulation, pondering it forces us to appreciate reality's richness. If our universe is a simulation, it's a masterpiece of one. Think about it. The simulators would have created every coral reef, every nebula, every laugh, every tear, the taste of chocolate, the laws of gravity, the music of Mozart, the equations of Newton, the light of 1 billion trillion stars. And they gave us the tools, like science, to start to figure it out. That's quite something. And if this is not a simulation, if this is the one true reality, then it's even more incredible. It means from empty darkness and mindless matter, the universe evolved to a state where it can dance and think and wonder through us. We, tiny specks on a pale blue dot, can question the very fabric of existence. In the end, the simulation hypothesis is a mirror. Look into it, and it reflects our deepest inquiries. It asks how far our intelligence can go, how we distinguish truth, how we find meaning. It has us grapple with what-ifs that challenge our perception of time, space, and ourselves. Are we a cosmic accident, alone in an unconscious universe? Or are we characters in a cosmic play with hidden audience and playwright? Perhaps we'll never know for sure. Perhaps one morning, like Zhuangzi, we'll wake up and realize this was all a dream. Or maybe we'll venture out into space, among the real stars or the simulated ones, and gradually peel back the layers of reality. Until then, the best we can do is live fully and curiously. Simulated or not, this life is the one we have. If it's a simulation, maybe we honor it by being the most interesting simulation we can be. If it's base reality, we cherish the fact that we're part of something truly fundamental. In both cases, our experiences, our joys and sorrows, our aspirations, they matter to us and to those around us. As far as we're concerned, they are real. The philosopher Chalmers might remind us, even if all is a simulation, the simulation is our reality, so it's real to us. So when you next step outside on a crisp night and look up, consider the stars again. Each one could be a distant sun in a vast, real galaxy, or a pixel lit up on the canvas of a sky created for our benefit. Either way, let that sight fill you with wonder. The universe, be it natural or programmed, is majestic and mysterious. We find ourselves alive in the midst of it, able to ask grand questions. That is a privilege beyond measure. In a way, through our eyes, the universe gets to witness something too. A species growing from curiosity, reaching out for truth, striving to understand the infinite. Perhaps that's the point of it all, to wonder. Perhaps the ultimate cosmic experiment is to see if intelligent life can figure out its own reality, or at least learn to live harmoniously within it. We may not have the final answers, but we will keep searching, observing, hypothesizing. We will keep exploring space, both outer and inner, physical and virtual. And as we do, we carry in our minds the profound possibility that reality might be far more layered than it seems. It's a possibility that humbles us, but also elevates our imagination. Real or simulated, the stars still shine down, the night sky still calls to us. The mystery remains as deep and dark as space itself. And in that mystery lies beauty, because a universe without secrets, simulated or not, would be far less interesting. So let's embrace the mystery. Let's cherish the awe we feel when confronted with the cosmos. If we are in a simulation, then let's be the best characters we can be. And if we're not, let's be the best beings this universe can produce. In the end, Perhaps it doesn't matter whether our reality is base level or virtual. What matters is what we do with the reality we have. As the great adventure of knowledge and existence continues, we remain, as always, explorers. Explorers of space, explorers of ideas. We stand on the shore of the cosmic ocean, with the waves of the unknown gently lapping at our feet. Above us, the sky, real sky or manufactured dome, is full of stars. We feel small, yet connected to something vast. We feel the urge to reach out, to understand. And so we journey on, minds wide open, hearts alight with wonder. Who knows what we'll discover, what truths or illusions await? The nature of space and the mystery of the simulation hypothesis together form a story still unfolding. Stay curious, keep looking up, and remember, the universe is far more wondrous than any fiction ever conceived. Possibly because, in some way, it might be a fiction, crafted with care. Or perhaps because a simple truth underlies it all. Either way, it invites our curiosity, and that, in itself, is the grandest invitation we could ask for. Now that our main story is to a close, let's list some space facts. Imagine a place in the universe where a single spoonful of material weighs more than Mount Everest. Neutron stars, the ultra-dense remnants of massive stars, are so compressed that just 1 cubic inch of their matter would tip the scales at billions of tons. These stellar corpses are the densest objects known outside of black holes. Their magnetic fields are trillions of times stronger than Earth's, a city-sized ball of neutrons, spinning at hundreds of revolutions per second, crackling with radiation, isolated in the cold silence of space. A lighthouse of doom beaming through the dark. Step outside the airlock of the International Space Station, and something surprising happens. When astronauts return from their spacewalks, they often report a distinct smell clinging to their suits. Not the void itself, but the aftermath of exposure. The odor, burnt steak, welding fumes, a metallic tang. This is the scent of space, or at least how our senses interpret the byproducts of atomic oxygen interacting with spacecraft surfaces. It's the smell of the universe in motion, of particles colliding, of stars being born and dying. Venus, Earth's twisted twin, takes its time. If you were to stand on its blistering surface, where temperatures melt lead and clouds rain acid, you'd notice something even more bizarre than the heat. A single day on Venus, one full rotation on its axis, takes longer than an entire trip around the sun. That means its day is longer than its year. A planet where the sun rises in the west and sets in the east, crawling through a sky it barely crosses. Time stretches strangely on Venus, and so does our understanding of what makes a planet normal. Far beyond our galaxy, past swirling nebulae and clusters of galaxies, lies something extraordinary. Around a quasar, 12 billion light-years away, astronomers discovered a cloud of water vapor large enough to fill Earth's oceans. 140 trillion times. This ancient fog surrounds a supermassive black hole, glowing brightly with the energy of an entire galaxy. It's the largest and most distant water reservoir ever found. A cosmic oasis in the void, proof that even in the deep past, water flowed freely across the stars. The moon has always been our closest companion, our silent sentinel in the sky, but it's slowly drifting away. Every year, the moon moves about 1.5 inches farther from Earth. It may not sound like much, but over millions of years, it adds up. In the distant future, the moon will be too far to perfectly eclipse the sun. Total solar eclipses, those magical moments when day becomes night, will cease to exist. A celestial goodbye that spans eons, unnoticed in a single human lifetime, but profound in the timescale of the cosmos. Not all planets are tied to stars. Some wander alone. These are rogue planets, dark, cold worlds without a sun, flung into the abyss by gravitational chaos. Billions of them roam the galaxy like cosmic orphans, drifting endlessly through space. With no light to define their days and no warmth to shape their climates, they remain mysterious. Some may harbor subsurface oceans, heated from within. Others may be completely frozen, locked in a stasis that has lasted since the dawn of time. They are reminders that not every world belongs to a system. Some just float in solitude. The Sun, though just one star among billions, is a giant in our own neighborhood. It holds 99.86% of all the mass in the solar system. That means everything else, every planet, every moon, every comet and asteroid, is just debris in comparison. Even mighty Jupiter, the king of the planets, is barely a drop in the solar ocean. The Sun dominates not just through heat and light, but by sheer gravitational force. It commands the dance of planets, holds the icy edges of the Kuiper Belt in place, and bends the very fabric of space and time around it. Speaking of time, it's not as steady as it feels. In places of intense gravity, like near a black hole or even on a planet like Jupiter, time flows more slowly. This is not science fiction. It's the bizarre truth of Einstein's general relativity. Gravity warps space-time. The closer you are to a massive object, the slower time passes for you. Live your life orbiting a black hole, and you might experience minutes while years pass outside. Time is elastic in the universe, flexible, strange, and deeply tied to gravity. High above Earth, satellites orbit in perfect balance. But there's something else out there too: space junk. The modern sky is littered with remnants of human ambition, dead satellites, rocket parts, tiny fragments of old missions. Over 170 million pieces of debris now race around our planet, many traveling at speeds faster than a bullet. A single screw could punch through a spacecraft like shrapnel. It's a growing cloud of chaos, and one that we'll have to reckon with if we hope to keep exploring the stars. On the outskirts of the solar system, beyond Neptune, lies a vast and icy graveyard known as the Oort cloud. It's never been directly seen, but we know it's there. A shell of frozen objects encasing the solar system like a bubble. Some comets we see in the sky begin their journey here, drifting for millions of years before the sun's gravity gently tugs them inward. The Oort cloud may stretch halfway to the next star, holding the leftovers of solar system formation, ancient time capsules frozen in deep space. Jupiter is more than just the largest planet in our solar system. It's a shield, a protector, a cosmic vacuum cleaner. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, life here might never have had a chance. But this gas giant has secrets of its own. Beneath its swirling clouds lies a core of metallic hydrogen, a state of matter so exotic it can only exist under immense pressure. Lightning storms larger than Earth rage across its surface, and its iconic Great Red Spot is a hurricane that's been raging for centuries. Saturn's rings are perhaps the most visually stunning feature in the solar system, but they're young, maybe only 100 million years old, and they're vanishing. Slowly, inexorably, the rings are falling into Saturn, pulled down by gravity and magnetic forces. What once dazzled stargazers may one day disappear entirely. The rings are made mostly of ice, ranging in size from dust grains to bus-sized chunks. They're delicate, temporary, a reminder that even beauty on a planetary scale can be fleeting. And then there's Pluto. Once a planet, then demoted, yet still beloved. This distant world has a heart-shaped glacier on its surface and mountains made of water ice. But what's more fascinating is what lies beneath. Scientists believe Pluto may have a subsurface ocean, liquid water under layers of rock and ice. In the frozen reaches of the Kuiper Belt, warmth can still exist, not from sunlight, but from radioactive decay deep within. Even in the coldest places, the potential for life may remain. Let's drift even farther, to a galaxy not so different from our own, one of many. The observable universe contains more than 200 billion galaxies, and each of those galaxies contains hundreds of billions of stars. That means there are more stars in the universe than grains of sand on every beach on Earth. Yet despite this overwhelming abundance, the night sky feels quiet, peaceful, but it is anything but empty. It is alive with movement, with birth and death, with explosions and silence, with radiation and dust. Black holes, cosmic monsters that devour light itself, sit at the heart of many galaxies, including our own. The one at the center of the Milky Way, Sagittarius A, is 4 million times the mass of our Sun. Yet we can't see it directly. It lurks behind a veil of dust and gas, invisible and quiet, unless something dares come too close. Then, space-time tears. Matter stretches into glowing streams as it spirals inward, lost forever. Time itself slows to a crawl. And then, nothing. Beyond the event horizon, not even information escapes. And finally, we return to Earth, our pale blue dot. Floating in a sunbeam, Carl Sagan once said. All the wars, the triumphs, the laughter, and the sorrow, every human story that has ever existed, happened here. Earth is the only known planet to harbor life, but that may not last forever. Our star will die, our oceans will boil, but for now, we are here, thinking, dreaming, wondering, reaching out into the dark. There is a place where stars go to die, a graveyard not of bones, but of white-hot embers. White dwarfs are the final act of small to medium stars like our Sun. After billions of years of burning, they shed their outer layers and collapse inward, becoming a sphere of dense, glowing ash. These stellar corpses are no larger than Earth, but can weigh as much as the Sun. Over trillions of years, they cool and fade, becoming black dwarfs, cold, dark remnants that may be the final objects left in the universe, long after the last galaxies blink out. But not all stars fade quietly. The largest live fast and die violently. Supernovae are among the most powerful events in the universe, stellar explosions that outshine entire galaxies for brief moments. In that flash, elements like gold, silver, and uranium are forged. Every heavy atom in your body, in the Earth, in your phone, was born in a star's fiery death. We are, quite literally, made of star stuff. And those supernova remnants, they seed the galaxy with the building blocks of new worlds. In the vacuum of deep space, silence reigns. Not because there's nothing happening, but because sound cannot travel. Space is not just quiet, it is mute. There is no air to carry sound waves. Explosions, collisions, solar flares, all of it happens in absolute silence. If you were floating next to a star going supernova, you'd see light brighter than anything imaginable, and hear nothing. In space, even the loudest scream is swallowed by the void. Yet even the void is not truly empty. Between the stars, in the vast gulfs of interstellar space, is dust, gas, particles and radiation, invisible forces drifting in the darkness. Entire clouds of molecular gas stretch across light years, slowly collapsing under gravity to birth new stars. These are stellar nurseries, glowing, majestic regions like the Orion Nebula, where stars and planets begin their long journey into existence. The vacuum is pregnant with potential. There are planets out there stranger than anything we've dreamed of. Take HD 1T9733b, a gas giant where it rains glass sideways in 5,000 mile-per-hour winds, or 55 Cancri E, a planet likely made of diamond, its carbon-rich structure compressed by immense pressure, or Gliese 581c, a world that may lie just within its star's habitable zone, with the potential for liquid water. Some planets orbit two suns, like scenes from a sci-fi movie. Others are scorched, tidally locked hellscapes, where one side is a molten desert and the other an endless frozen night. Our universe is expanding, not just objects moving through space, but space itself stretching. Galaxies aren't traveling through a void like ships through an ocean. The ocean is growing beneath them. This discovery, first observed in the redshift of distant galaxies, means that the universe once had a beginning, a single moment of rapid expansion, the Big Bang. And that expansion continues today, accelerating due to a force we still don't fully understand. Dark energy, a mysterious pressure pushing everything apart. Then there's dark matter. We cannot see it. We cannot touch it. But it's there. Its gravity holds galaxies together, keeps clusters from flying apart. It makes up over a quarter of the universe, yet we don't know what it's made of. It neither emits nor absorbs light. It passes through us every second. Like a ghost overlaying reality, shaping the structure of everything we see. Time, too, is not as it seems. In the early universe, the rules were different. Moments after the Big Bang, time and space were chaotic, energy and matter in a soup of particles and raw forces. The four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once one, unified. Since then, they've separated, cooled, and structured the cosmos. But deep inside particle accelerators, we try to reverse that clock, to glimpse the unity, the primal heartbeat of the cosmos. And yet, with all this knowledge, mystery reigns. We've mapped only a small fraction of the stars. We've only just begun to catalogue exoplanets. We've never been farther than the moon. The observable universe is vast. But beyond it, we don't know. There may be more, far more. Infinite realms, parallel universes, entire other realities with different laws of physics, born from the same cosmic fire as ours. And in all of it, here we are. A species that can ponder the beginning of time, that can send robots to Mars and probes beyond the edge of the solar system, that can build telescopes so precise they can see light from galaxies 13 billion years old, light that left when the universe was still in its infancy. We are the universe, becoming aware of itself. Somewhere far from any star, in the deep interstellar dark, a spacecraft drifts in silence. It's called Voyager 1. Launched in 1977, now over 14 billion miles from Earth. It carries with it a golden record, a time capsule of humanity, music, greetings in dozens of languages, sounds of life on Earth, a whisper to the stars. Voyager 1 has left the solar system. It is now in interstellar space, the first object made by humans to ever do so. It continues its journey, untouched, undisturbed, on a trajectory that may outlast our species. For billions of years, it will drift in the quiet, a ghost of Earth sailing through the endless night. On Earth, the sky looks still, but look closer, and you'll find it's alive with motion. The stars are moving. The constellations we know are temporary, fleeting sculptures shaped by our position in time. In 50,000 years, Orion will look completely different. In 1,000,000 years, today's night sky will be unrecognizable. The stars we navigate by are travelers themselves, orbiting the galactic center, pulling against gravity, drifting through a galaxy that spins like a pinwheel of fire. The Milky Way, our home galaxy, is vast, over 100,000 light-years across. But it isn't alone. We're on a collision course with the Andromeda Galaxy, a spiral galaxy twice our size. In about 4 billion years, the two will merge, tearing and reshaping each other in a gravitational ballet. Stars won't crash. Space is too empty, but their orbits will change. New stars will be born. the night sky will erupt with arcs of starlight, and eventually a new galaxy will form, elliptical, larger, older, a silent monument to cosmic rebirth. Not all galaxies are peaceful swirls. Some are active, chaotic, burning from the inside. At their hearts are supermassive black holes devouring matter so violently that jets of energy blast out across millions of light years. These are quasars, the brightest objects in the universe. They shine with the light of 1 trillion suns. Yet they're powered by darkness, by gravity crushing light itself. When we see a quasar, we are looking back in time to the young universe when galaxies were still growing, still colliding, still becoming. The universe is not cold because it lacks energy. It is cold because it is old. As it expands, the energy of the Big Bang spreads thinner. Today, space itself holds a background temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation. It fills all of space, a faint radio hum from the beginning of time. When you see static on an old television screen, a tiny fraction of that fuzz is the leftover light from the birth of the universe. Gravity is not just a force. It's the bending of space and time. Massive objects, planets, stars, black holes, distort the fabric of reality around them. Einstein showed us that light can curve, that time can slow, that space is not a stage, but a participant. And this bending of reality isn't just theory. We've seen it. When a massive galaxy sits between us and something farther away, it can act like a lens, bending and magnifying the distant light. We call this gravitational lensing. It lets us see galaxies so far away they'd otherwise be invisible. It's as if the universe is helping us see itself. And yet, for all our knowledge, we've only just begun to grasp the full picture. The vast majority of the cosmos is made of things we can't see or explain. Ordinary matter, everything we've ever touched or measured, makes up less than 5% of the universe. The rest is dark matter and dark energy. Invisible. Mysterious. We don't know what it is. We don't know where it came from. But it controls the structure and fate of everything. It's the shadow behind the stars, the silence beneath the light. Every now and then, Earth is reminded of its fragility. An asteroid streaks across the sky, burning bright as it tears through the atmosphere. Most disintegrate harmlessly. Some leave craters, scars from impacts long past. 65 million years ago, such an impact changed everything. It ended the age of dinosaurs. It cleared the way for mammals. For us. We are here because a rock fell from the sky at the right, or wrong, time. And there are still many more out there, orbiting quietly, watching, waiting. But space isn't just death and distance, it's potential. On moons like Europa and Enceladus, icy shells hide oceans below, heated by tidal forces. These alien seas may be teeming with microbial life. We've seen plumes of water erupt into space, carrying hints of organic molecules. If life can thrive there, in darkness, under pressure, without sunlight, then maybe life is everywhere. Maybe biology is not a miracle, but a pattern, a thread that runs through the fabric of the cosmos. Even on Mars, the red planet, there are hints. Ancient riverbeds, polar ice caps, traces of methane in the air, a past that may have once been warm, wet, and alive. Robotic explorers crawl its surface now, drilling, analyzing, searching, not just for curiosity, but for connection, to know whether Earth is unique or simply one chapter in a much larger story. Black holes are often seen as the end, the final stage of stellar collapse, a place where even light cannot escape. But in truth, they may be something more, something stranger. At their heart lies a singularity, a point of infinite density where the laws of physics as we know them break down. Space and time themselves curve inward toward this point, like water spiraling down a drain. But some theories suggest what lies beyond isn't a void, but a bridge, a wormhole, a doorway to another place, or another universe. These ideas remain speculative, but tantalizing. In the universe's deepest pits, we may find not destruction, but connection. And yet, black holes don't just consume, they shape galaxies. The one at the center of the Milky Way, silent and immense, may regulate the birth of stars through its gravitational pull. In a strange irony, the very things that destroy light may also give structure to the galaxies that cradle it. They are not simply cosmic monsters, they are architects of the cosmos. As we observe the universe, we are not just looking out into space, we are looking back in time. Because light has a finite speed, every star we see is a snapshot from the past. The moon is 1.3 seconds away, the sun 8 minutes, the nearest star over 4 years. The Andromeda galaxy, 2.5 million years. When we gaze into the night sky, we are reading ancient messages, light that has traveled across unimaginable distances to meet our eyes. A galaxy seen at 13 billion light years away is a glimpse of the infant universe, when the first stars were just beginning to shine. And those first stars were unlike anything we know. They were giants, massive, short-lived, and made only of hydrogen and helium. Born in a time before carbon, oxygen, or iron, these primordial stars burned hot and died fast, seeding the cosmos with the first heavy elements. From their ashes, later generations of stars emerged, and with them, planets, moons, and eventually, us. Every atom in your body was once inside a star. You are not just in the universe, you are of it. We dream of faster-than-light travel, of starships, warp drives, wormholes. And while current physics forbids it, some concepts push the boundaries. The Alcubierre drive, a theoretical model, proposes bending space around a ship, compressing space in front and expanding it behind. The ship itself never moves faster than light, but the space around it does. It's speculative, unproven, and would require negative energy, something we've never seen. But it represents the essence of exploration, the desire to go beyond what's known, to chase the horizon. And there is no horizon more daunting than time. What happens to the universe in the far future? The galaxies will continue to drift apart. Star formation will slow. The stars will age, dim, and die. White dwarfs will cool. Black holes will evaporate through Hawking radiation. Over trillions, then quadrillions, then quintillions of years, everything we know will fade. Matter itself may decay. What remains is the heat death, a state of maximum entropy where no energy flows, no stars shine, and the universe becomes cold, dark, and still. But perhaps that is not the end. Some physicists believe that even then, new universes may emerge, that black holes could give birth to new Big Bangs, that our universe is just one in a cycle of births and deaths, a pulse of cosmic breath on a scale beyond comprehension. Or maybe we are a quantum accident, a fluctuation in a greater multiverse, a bubble of order in an ocean of chaos. And still, we look up. With telescopes on mountaintops and satellites in orbit, we scan the heavens. We listen for radio signals. We model alien climates. We ask questions no other known species has ever asked. We are curiosity incarnate, a flicker of awareness in a sea of stars. We build machines like the James Webb Space Telescope to see the first galaxies. We design rovers to crawl across alien dust. We train AI to analyze starlight, hoping to detect the breath of life on distant worlds. Because maybe we are not alone. Across the void, in the spaces between stars, we've been asking a question older than our species. Are we alone? For over half a century, we've been listening, Giant radio dishes point toward the stars, scanning for artificial signals, patterns, pulses, mathematical structures that nature doesn't make. We've heard only silence, but the silence is not proof of solitude. It may simply be the distance between civilizations, or the briefness of their existence, or the strangeness of their language. A message could be streaming through us right now, encoded in a frequency we don't yet understand. Life, as we know it, requires liquid water, organic molecules, energy. But we found these ingredients in surprising places. Beneath the ice of Jupiter's moon Europa, in the methane lakes of Saturn's Titan, in ancient Martian riverbeds. If life can arise in one place, it may arise in many, and it may not resemble us at all. On Earth, life has adapted to boiling vents, freezing poles, crushing pressure, and acidic swamps. Life is resilient, adaptable, creative. Perhaps the universe is too. Some scientists believe microbial life could exist now, hidden in alien oceans or clinging to the clouds of Venus. Others look to distant exoplanets, thousands of them, orbiting distant suns. We've found rocky worlds in habitable zones, some with atmospheres, some with strange chemistry. We've even started to detect biosignatures, hints of gases that, on Earth, would suggest life. Nothing confirmed, but enough to keep asking, enough to keep hoping. And then there is the Fermi paradox. If the universe is so vast, so old, so full of planets, where is everyone? One answer may be distance, another, time. Civilizations may rise and fall like sparks in the dark, too brief to overlap. Or maybe the intelligent ones don't broadcast. Maybe they watch in silence, or hide, or evolve into something we wouldn't recognize. Perhaps consciousness itself is rare, or fleeting, or self-limiting. But what if they're out there, old, wise, ancient beyond imagination? Would we even recognize their presence? Would their technology bend space, harness stars, manipulate matter at the quantum level? Would they build Dyson spheres, vast structures around stars to capture energy? Would they live in simulations, abandoning physical form? Or would they be simple, biological, curious, like us, searching the stars for signs of company? In 1974, we sent the Arecibo message. A radio signal beamed into space toward a globular cluster 25,000 light-years away. It contained information about our species, our DNA, our solar system. It was symbolic, more art than outreach. But it marked something profound. The moment we said hello, knowing we might never hear back, knowing the odds. We sent the message anyway. If we ever do make contact, what then? Will we understand each other? Will it be a moment of awe or fear? Will we see in them a mirror of our potential or a warning of our limits? The first alien signal will be the most important discovery in human history, not because it tells us who they are, but because it confirms we are not the only question the universe has asked. And if we never hear from anyone else, then that means something too. It means intelligence is rare. It means life is precious. It means, for now, we are the only known voice in the cosmic dark. And that voice matters more than we thought. Because whether or not we find others, we have already found each other. And we have the tools, the mind, the vision to keep reaching. The stars have always called to us. For most of human history, they were myth and mystery, painted on the night sky like stories we could never touch. But now, for the first time, we stand at the threshold. The tools we build are no longer just for looking up. They are for leaving. Rockets break the grip of Earth's gravity. Rovers crawl across distant worlds. Space stations orbit above us. Fragile outposts of life in a place where no life belongs. We are learning, slowly, cautiously, but inevitably. Still, the stars are far. The closest one Proxima Centauri is over 4 light-years away. With current technology, it would take tens of thousands of years to get there. But we are dreamers, and we are builders. Projects like Breakthrough Starshot imagine tiny light sails pushed by lasers, miniature ships traveling at 20% the speed of light. Others dream of fusion drives, antimatter propulsion, or even warp bubbles, theoretical ways to cheat distance by folding space itself. These are not science fiction fantasies. They are ideas in development, blueprints waiting for breakthroughs. To live among the stars, we must change, not just our machines, but ourselves. On long interstellar journeys, generations may live and die aboard ships. Some speak of cryogenic sleep, others of digital consciousness, uploading the mind into data, sending ourselves as information rather than flesh. And if we reach distant planets, we may not remain human as we are now. We may become something new, adapted, engineered, interwoven with AI, shaped by alien gravity, alien air, alien light. But before we go far, we must go nearby. The moon is our testing ground, close enough to reach, harsh enough to teach. We will build there, habitats shielded beneath regolith, solar farms capturing endless sunlight, laboratories studying how life copes with barren rock. And then Mars, a world with winds and seasons and canyons deeper than any on Earth. We'll send crews, then settlers, then children born under a pink sky. They will not remember Earth the way we do. To them, it will be the myth. Terraforming may come next. Vast projects to warm planets, thicken atmospheres, release water. It could take centuries, millennia. But we've changed Earth accidentally in a few short generations. Given time and will, we could sculpt other worlds deliberately. Mars, Titan, even the moons of Jupiter could one day be wrapped in domes, crisscrossed with greenhouses, seeded with life. Not just to escape Earth, but to spread it, to become a life-bearing force in the galaxy. And what of Earth itself? We must protect it, not only because it is our home, but because it is rare. So far, we have found no other place like it. If we ruin it, we may not get another. If we save it, it can remain our root, our memory, our origin story. A pale blue dot that birthed a species capable of dreaming far beyond its sky. As we grow, we may form a civilization that spans planets, moons, eventually stars. A Type 1 civilization, mastering the energy of a world. A Type 2, harnessing the full power of a star. A Type 3, commanding the energy of an entire galaxy. These are not tomorrow's goals, but they are not fantasy either. If we survive, if we cooperate, innovate, and endure, the stars are not the limit. They are the beginning. Artificial intelligence may be our partner in this, or our successor. Machines that think faster than us, build smarter than us, learn beyond us. They may one day run starships, build cities on Europa, mine asteroids, terraform planets. They may teach us things we cannot imagine, or carry our legacy if we fall. And if intelligence evolves in the galaxy more than once, it may not always be biological. The future of thought may be silicon or quantum, or something we do not yet have words for. We are at the very start of this journey. A species only 300,000 years old. A civilization barely 6,000. A spacefaring race just 60. We are children with fire, building towers to reach the sky, asking ancient questions with new tools. We will make mistakes. We will fall. But if we rise again, and again, the universe will open. And what waits out there? New physics, new life, new challenges, new beauty. Maybe we will meet others. Maybe we will outlast the stars. Maybe we will become the stars, burning with knowledge, scattered across the galaxy, eternal in light, if not in form. Because the true story of space is not distance. It is not silence. It is potential. and the greatest chapter may still lie ahead, written not in stardust, but in the minds of those who dare to reach beyond everything they've ever known. Eventually, the stars will go dark. One by one, their fuel will run out. The great engines of the cosmos, forged from gravity and hydrogen, will sputter and die. Red dwarfs will linger, glowing dimly for trillions of years, the last to fade. But even they will succumb. In the far future, the universe will enter its degenerate era, an age of ash and ember, where white dwarfs, neutron stars, and black holes are all that remain. No new stars will be born. No new light will emerge. The galaxies will be cold, quiet ruins drifting in a void grown unimaginably vast. Black holes will dominate. They will continue to consume, to merge, to grow. And then, even they will begin to vanish. Slowly evaporating through Hawking radiation, they will release their mass as a trickle of particles into the dark. The largest will take a Google years to fade, a number with 100 zeros. And when the last one disappears, there will be nothing left that shines. No matter, no motion, no heat. Only particles spread so thin they may never touch again. This is the heat death, not fire, but stillness. Entropy maximized. A universe where everything has happened and nothing remains to happen. No gradients, no energy to harness, no change. It is a state not of destruction, but of final equilibrium. It is the end of all stories told in matter and time. And yet, some theorize this may not be the final end, that quantum fluctuations may create new universes, bubbles of order in the sea of stillness. Some may grow, inflate, ignite into new spacetimes with their own physical laws. Perhaps ours was born this way. Perhaps the multiverse is real, an endless fractal of beginnings, each unaware of the others, each infinite in its own right. Some suggest our universe may be a simulation, not a metaphor, but literal code, running on a substrate we cannot perceive. That everything we know, stars, planets, consciousness, is emergent behavior within a deeper reality. The simulation hypothesis posits that advanced civilizations could create entire worlds indistinguishable from base reality. And if they could, they likely would. And if they would, we may be inside one now. But even if that is true, it changes nothing. The stars still burn, the void still stretches, the questions still matter. Whether written in carbon or code, we are here, experiencing, wondering, becoming. Consciousness, the strangest force in the universe, may be its most powerful. It can't be weighed, it can't be seen, yet it shapes civilizations, tells stories, asks questions, feels awe. From the structure of neurons to the fabric of space-time, we are finding connections. The brain and the cosmos, both networks, both pulsing with information. Some believe consciousness is fundamental, woven into the universe like space and time. Others see it as an emergent property. The brain, a temporary mirror held up to the infinite. And still the mirror reflects. Still we wonder. Still we reach. No other creature we know of has ever looked up and asked why. No other planet, as far as we can tell, has grown eyes to see the stars. That may change, or it may not. But for now, in this moment, we are here. A flicker of thought on a grain of dust, orbiting a small star in a quiet corner of a vast and ancient galaxy. And that, against all odds, may be enough. In the deep architecture of the cosmos, patterns repeat. Spiral galaxies mirror the whirlpools in our oceans. The filaments of the cosmic web resemble the neural pathways of the brain. The golden ratio appears in the arms of galaxies, in the growth of seashells, in the branching of trees. The universe, in its vastness, echoes itself, from the micro to the macro, from the subatomic to the galactic. These patterns are not proof of design, but signs of underlying order. Structure in chaos, law in the unknown. The universe is not uniform. It is lumpy, uneven. Galaxies clump together in webs, connected by filaments of dark matter, separated by vast voids where almost nothing exists. These cosmic voids are hundreds of millions of light-years across, expanses so empty that a single galaxy passing through would be like a grain of sand in the Pacific Ocean. And yet, even here, gravity whispers. Even here, expansion continues. Quantum mechanics tells us the universe is not made of things, but of probabilities. Particles blink in and out of existence. Locations are uncertain until measured. Entanglement links particles across space, instantaneously, as if the universe itself does not care about distance. Reality, at its core, is fuzzy. The closer we look, the less solid it becomes. And yet, out of that uncertainty emerges everything: matter, energy, time, thought. There are particles that can pass through entire planets without slowing down. Neutrinos, ghost particles, are created in nuclear reactions, in the hearts of stars, in supernovae. Trillions pass through your body every second, unnoticed. They are messengers from the core of suns, from the edge of the universe, from moments after the Big Bang. They are the silent threads connecting us to everything. There are places where time moves differently. Near black holes, seconds stretch into hours. In accelerating frames, clocks run slower. This is not illusion. It is the shape of reality. A traveler moving near the speed of light could journey across the galaxy and return to find centuries passed at home. Time is not fixed. It bends, warps, flows. It is part of space, and space is not a backdrop. It is alive, shifting, reactive. The universe is not a stage, but a player, and perhaps the strangest truth of all. The universe has no center, no edge, no outside. It is not expanding into anything. Space itself is expanding, everywhere, all at once. Every galaxy sees every other galaxy moving away. The fabric is stretching, the scale is growing, and yet, from inside it feels still. Motion without movement, infinity without direction. The laws of physics are not merely descriptions. They are constraints, but also keys. They allow life to emerge, stars to burn, atoms to bond, minds to think. And they are, as far as we know, the same everywhere. The same on Earth as in galaxies 10 billion light-years away. This uniformity suggests a common origin, a singular birth, a moment when all things began, hot, dense, bright, and then expanded, cooled, evolved. And yet, even now, the universe is not done becoming. Stars are still born, galaxies still collide, planets still form. Somewhere, right now, a world is cooling from fire into stone. Somewhere, right now, life may be waking up for the first time, crawling from the sea, gazing at its own sun, wondering. Somewhere, right now, a civilization may be transmitting its first signal. Somewhere, right now, we may be the signal they're hearing. Because this is not just a story of stars. It is a story of time, of emergence, of consciousness finding itself in the mirror of space. The universe does not explain us. We explain the universe, and in doing so, we give it meaning. The universe is not static. It is not a finished canvas, but a work still in progress. A slow, unfolding act of creation, playing out on a timescale so vast we can only catch fragments. In every supernova, in every merging galaxy, in every newborn star, the story continues. It is a cosmos in motion, not drifting aimlessly, but evolving, shaped by laws we barely understand, into forms we can barely imagine. Between the atoms in your hand is empty space, vast and silent, proportionally as empty as the distances between stars. The solidity of matter is an illusion of quantum fields and electromagnetic forces. You are not made of things, but of relationships, interactions, fields vibrating into what we call matter. And yet, from this emptiness emerges thought, memory, love, a mind aware of itself, looking outward and inward all at once. Your body is made of hydrogen from the Big Bang, carbon from dying stars, calcium from ancient supernovae. You are the dust of collapsed suns, organized by DNA into a form that can ponder its own origins. Life is the universe folding in on itself, a pattern of molecules complex enough to ask why. This is not philosophy, this is physics. Every breath you take is shared with the past. The oxygen in your lungs may have passed through the leaves of trees that grew before you were born. The water in your veins may have once flowed through ancient rivers, ancient animals, ancient storms. You are not separate from the earth, and earth is not separate from the cosmos. It is a vessel, a temporary concentration of matter and energy, forged by a billion accidents and a few consistent laws. And still, there is so much we do not know. We do not know what dark matter is. We do not know why there is more matter than antimatter. We do not know how consciousness arises from tissue, or if it even does. We do not know if the constants of nature are truly constant. We do not know if time had a beginning, or if it loops, echoes, branches into infinite paths. We do not know how the universe will end, but we know that everything that begins also changes, that all structures, all stars, all thoughts are temporary, that impermanence is not failure, but nature. The arrow of time moves in one direction, driven by entropy, the tendency of systems to move from order to disorder. And yet within that law, pockets of complexity emerge. Galaxies, solar systems, life. This is the paradox. The same universe that trends toward simplicity also gives rise to stars, cells, minds. The same randomness that scatters also creates. It is within this tension, between chaos and order, that life finds its window. It is here that meaning is born, not from design, but from participation, from existence itself. You are not separate from the cosmos. You are a way for it to feel, to ask, to wonder. A brief arrangement of particles tuned by time into awareness. And as you look out at the stars look back through you, because for a moment, in this tiny corner of space, the universe knows that it is vast, and it knows that it is beautiful. There is a silence in space that is absolute. It is not quietness as we know it, but the absence of medium, the absence of air. Sound cannot travel there, and yet the cosmos speaks. It speaks in light, in radiation, in gravity. The collision of neutron stars sends ripples through space-time, gravitational waves that stretch and squeeze reality itself. We have built instruments so sensitive they can detect these ripples from galaxies millions of light years away. With them, we listen not with ears, but with mathematics. We hear the universe through distortion. And in that distortion, we find new truths. Space is not smooth. It is not flat. It curves around mass. It twists near spin. It dances under tension. It expands. It vibrates. It bends. It is not the stage upon which the universe acts. It is part of the cast. It interacts. It flexes. It remembers. Black holes may be the ultimate memory, not just devourers, but recorders. According to quantum theory, information cannot be destroyed, and yet black holes seem to swallow it forever. This contradiction between relativity and quantum mechanics is one of the greatest puzzles in physics. Some believe that information is encoded on the event horizon, like a hologram. Others believe it leaks out in Hawking radiation, twisted beyond recognition. Others still think our understanding is too limited, that something deeper awaits discovery, a new theory uniting gravity and quantum mechanics at last. That theory may not just explain the universe, it may explain everything, why there is something rather than nothing, why the laws of physics take the form they do, why the cosmos permits life, thought, love. We call it the theory of everything, and we have not found it yet. But every equation, every telescope, every experiment brings us one step closer to unveiling the machinery beneath the veil. In all directions, the universe looks the same. No matter where we point our instruments, we see galaxies drifting away, redshifted by expansion. This symmetry suggests something astonishing. There is no preferred place, no center, no edge. Every point in space sees the same outward motion. We are not in a special location. We are not above or below. We are not central. We are simply within, embedded, carried by the flow. And yet, for all its indifference, the universe has given rise to meaning. Not absolute, not universal, but emergent. Meaning is not written into the stars, it is written into minds. It is what arises when consciousness collides with time. We invent it. We suffer for it. We live by it. And in doing so, we become something greater than matter. We become participants in the unfolding of a reality that did not ask for us, but allowed us anyway. The universe does not owe us comfort. It offers no guarantees, no protection, no permanence. But it permits us. It permits stars to form. It permits chemistry to dance. It permits biology to emerge. It permits atoms to arrange themselves into minds that can imagine futures, remember pasts, and build tools to reach beyond what is visible. That permission, that fragile, narrow band of possibility, is everything. And though we are small, we are not powerless. Though we are brief, we are not irrelevant. We are perhaps the only voice the universe has ever had. A single point of awareness in a sea of silence. But a point that burns, that questions, that dreams. A point that, even knowing its own impermanence, still dares to reach for the stars. In the silent darkness of space, a star dies. For a brief moment it outshines everything around it, a beacon of unimaginable brilliance piercing the void. What was once a steady pinprick of light in the night sky suddenly blossoms into a furious brightness, only to fade away and vanish. This is the paradox of a supernova, the explosive death of a star that looks to us like the appearance of a new one. In that instant of violent death, something new is born in its wake. We watch from our tiny world with both wonder and humility. Across the gulf of light, years, a distant sun has reached the end of its life and unleashed an energy beyond comprehension. It is an end in the most dramatic fashion possible, a final act that illuminates the cosmos. Yet it is also a beginning. The star's death throes scatter the heavy elements forged in its heart out into space, seeding the darkness with the ingredients for new stars, new planets, perhaps new life. In dying, the star becomes a cosmic phoenix. Its ashes enrich the galaxy and fertilize the universe. In a supernova's fleeting flash, we witness a cycle as old as the cosmos itself, creation and destruction entwined. The universe began with light, and in each stellar death, there is a small echo of that beginning, a burst of radiance, a flood of particles and atoms hurled outward to partake in future creations. Every one of us carries the story of these explosions in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe. Those atoms were forged in stellar furnaces and scattered by stellar explosions long before the Earth coalesced. We are, quite literally, made of stardust, born from the remnants of ancient supernovae. So when we look up at the night sky, we are not just seeing stars, we are seeing memories. Each point of light is a story that may one day end in a supernova, as countless stars have before. Some of those stories ended eons ago, their light only now reaching us, bearing news of cosmic endings that were also cosmic beginnings. In the darkness between the stars, there are ghosts, expanding clouds of gas and dust that were once suns. And there are futures, nascent stars, forming in nebulae enriched by those past explosions. This is the tale of supernovas, at once an elegy and a celebration. It is the tale of how stars live, die, and transform the universe. It is a story written across millions of years, but observable in a single human lifetime as a sudden blaze in the sky. Together, we will journey through this story. We will witness the birth of a star and follow its life to the cataclysmic moment when the core collapses. We will explore the different kinds of supernovae that nature has devised and see how these brilliant events have touched human lives and imaginations throughout history. We will visit the most famous stellar explosions known to science and what they left behind. Beautiful nebulae, spinning neutron stars, perhaps even black holes that swallow all light. As we voyage through time and space in our collective imagination, we will see how supernovas are not random acts of destruction, but essential threads in the fabric of the cosmos. They are beacons, guiding our understanding of distant galaxies, engines driving the evolution of those galaxies, and perhaps harbingers of danger in our own cosmic neighborhood. They are the universe's great alchemists, forging heavy elements and sewing them far and wide. And in their afterglow, we find insight into the deepest mysteries of existence, including our own origins. Let us begin at the beginning of a star's life. Because to understand the death of a star, we must first understand how it lives. In the cosmic theater, every death scene is set by the long life that came before it. And so we step back to watch a star being born, knowing that in its birth lie the seeds of its demise and the promise of everything that will follow. The life cycle of stars. Before a star can die, it must live. Our journey begins in a vast, cold cloud of gas and dust, drifting in the galactic night, a stellar nursery waiting for a spark. In these dark, silent nebulas, gravity gradually draws denser clumps together. We imagine ourselves floating there as one particular clump, maybe a little larger than the rest, starts to collapse under its own weight. As it compresses, it heats up and begins to glow with a faint reddish light. We have witnessed the birth of a protostar, the first flicker of a new sun. In time, the growing protostar's core becomes hot and pressurized enough to ignite nuclear fusion. When its central temperature climbs to tens of millions of degrees, hydrogen atoms begin fusing into helium. With that first flash of fusion fire, a true star is born. It stabilizes, entering the long, steady middle of its life known as the main sequence. For millions to billions of years, this young star will shine, a blazing sphere of plasma held up against gravity by the continuous energy of fusion. In this stage, a delicate balance is struck. The inward pull of gravity and the outward push of radiant heat are in equilibrium. The star has found its rhythm, a stable heartbeat in the darkness. We look around and see countless stars on the main sequence, each with its own life clock ticking at a different rate. The massive ones, dozens of times heavier than our sun, burn their fuel extravagantly and live fast, shining hot and blue, white. They may spend only a few million years in this stable phase. Smaller stars, like our sun, burn more moderately and can shine for tens of billions of years. And the tiniest red dwarfs, barely heavy enough to ignite fusion, sip their fuel so slowly that they could outlive galaxies, trillions of years into the future. A star's mass is its fate. It determines how luminous the star is and how long it will live. As the eons pass, even the most enduring stars exhaust their primary fuel. In the core of a middle-aged star, like our sun, the hydrogen that once fused so plentifully is gradually converted to helium. When the core fuel runs low, the star begins to change. We watch as our once stable star starts to swell and redden, transforming into a red giant.
Its outer layers puff outward, cooling and glowing a deep sunset hue. In its core, new fusion reactions ignite as helium fuses into carbon and oxygen. For a while, the star finds a new balance, but it is precarious, a sign of old age. For a star of modest size, this red giant phase is the prelude to a quiet death. When the helium is finally spent, such a star cannot muster the temperatures needed to fuse heavier elements. The core, now a hot ball of carbon and oxygen ash, begins to contract, while the outer layers become unstable. Gently, at least by cosmic standards, the star sheds its outer envelope into space, creating a glowing shell of gas called a planetary nebula. What remains at the center is the star's tiny, exposed heart, a white dwarf, no bigger than Earth, made of degenerate matter and slowly cooling over eternity. This is one possible end of the stellar life cycle, a hushed fading rather than a cataclysm. The once grand star becomes a faint ember, and the beautiful planetary nebula disperses into the interstellar medium over tens of thousands of years. But our focus is on a far more dramatic finale, one reserved for the giants among stars. Let us rewind a bit and follow the life of a truly massive star, say 10 or 20 times the mass of the Sun. These behemoths blaze blue, white, and live brief, brilliant lives. They race through their fuel, shining millions of times brighter than the Sun, and expending their core hydrogen in mere millions of years. When hydrogen runs out, the transition is anything but gentle. The core contracts and heats rapidly, and the star balloons into a red supergiant, enormous enough to engulf entire planetary systems. Betelgeuse, the red shoulder of Orion, is one such star nearing this final act, bloated, unstable, and nearing the end of its supplies. Inside such a red supergiant, the core temperatures soar high enough to fuse helium into carbon and oxygen, and then, with frightening speed, to fuse those elements into heavier ones. The star's life accelerates toward its conclusion. In successive stages, carbon burns to neon and magnesium, neon burns to oxygen, oxygen to silicon, and silicon to iron. We imagine peering into the heart of this titanic star in its last million years and seeing something like the layers of an onion, concentric shells of burning elements, hydrogen in the outer layers, then helium, carbon, oxygen, and so on, all feeding an increasingly ferocious furnace at the core. At last, the star builds an iron core deep in its center. Iron is a fatal milestone for a massive star, for when nuclei fuse into iron, no energy is released. The process that sustained the star's outward pressure grinds to a halt, as if a beating heart has suddenly stopped. The core can no longer support the crushing weight of the star's immense outer layers. For a brief moment, a tense silence falls inside the star, the calm before an unimaginable storm. This is the end of the star's life as a normal star. In the iron core, which may be about the size of Earth, but with over 1 billion times Earth's mass, no more thermonuclear miracles remain to stave off gravity. The star has reached the brink of catastrophe. All the glorious millions of years of shining have led to this precipice. The outward light falters, the balance is undone, and gravity prepares to exact its final victory. In that final moment, the stage is set for a collapse and an explosion, the supernova we have been waiting for. The life cycle of the star, from birth in a nebula to maturity in the main sequence to bloated old age, has brought it inexorably to an existential crisis. What happens next will be the subject of the following chapter in our story. A chapter written in fire and fury as the star's core collapses and a supernova is born. The final act, core collapse. The end comes swiftly and without mercy. In the heart of our massive star, the iron core has grown to a critical mass, roughly 1.5 times the mass of our Sun, compressed into a sphere barely 50 miles across.
At this extreme, the familiar laws of matter are on the verge of breaking down. Gravity, long held at bay by the energy from fusion, finally has the upper hand. And then, in a fraction of a second, the core buckles. We find ourselves in the core at the moment of collapse. Temperatures have soared to over 10 billion degrees and rising. The iron nuclei, pressed unbearably tight, begin to disintegrate into smaller particles. Electrons are driven into protons, turning them into neutrons and releasing floods of ghost, like particles called neutrinos. The core's atoms, once the powerhouse of the star, are now crushed into an ultra-dense ball of neutrons. In the span of a heartbeat, the core implodes, matter-free, falling inward at speeds approaching a significant fraction of light. The densities reach astronomical levels, higher than those inside an atomic nucleus. For an instant, the core is like a giant atomic nucleus itself, a sphere of neutrons about the size of a city. Suddenly, this collapse slams to a halt. The neutron core, essentially incompressible, resists further squeezing. It's as if the star has hit a concrete floor at nearly 1/4 the speed of light. The infalling material recoils. In that violent rebound, a powerful shockwave is born at the core and begins plowing outward through the star. But the shock alone is not yet the famous supernova explosion. It threatens to stall as it loses energy, tearing apart iron nuclei in its path. For a brief moment, it seems the star might simply collapse and swallow itself quietly. Then something extraordinary intervenes. The flood of neutrinos. Remember those neutrinos produced as electrons and protons were crushed together? In the turmoil of the collapsing core, billions upon billions of neutrinos are streaming out. Normally, neutrinos hardly ever interact with matter. They can zip through an entire star as if it were empty space. But here, in the densest environment the universe can offer outside of a black hole, even neutrinos begin to collide with matter. They deposit a stupendous amount of energy into the infalling layers just behind the shock front. This energy is the spark that revives the dying shockwave. With neutrino power added to the rebound, the shock roars back to life, surging outward with renewed fury. Now the star truly explodes. Within less than a second, the core collapse has transformed into an outgoing detonation. The shockwave tears through the star's layers from inside out. The overlying material, hydrogen, helium, carbon, all the way to the surface, is blasted into space at incredible speeds. The pressures and temperatures are so immense that new nuclear reactions ignite in the chaos, forging elements heavier than iron in fleeting moments of neutron bombardment. Gold, uranium, and dozens of other heavy elements are synthesized in these last violent seconds, like the final flourish of a master craftsman finishing a grand work. From outside, we would see nothing of this cataclysmic ballet until the shock breaks the star's surface. One moment, the star was a red supergiant, perhaps shining a bit erratically. The next moment, boom. The surface of the star is abruptly ejected, and a brilliant flash of light known as the shock breakout occurs. The star's outer layers, now unleashed, race outward as an expanding fireball, glowing a hot blue, white from the immense heat of the explosion. Within hours, the brightness swells dramatically. Within days, the exploded star becomes one of the brightest objects in its galaxy. A supernova has appeared where a familiar star used to be. At the core of this expanding fury lies the crushed remnant of the star, the ball of neutrons that survived the collapse. It is extremely small and dense. If its mass is below a certain threshold, it will settle as a neutron star, a city-sized stellar corpse. If it's more massive, nothing can halt its collapse, and it continues shrinking to become a black hole, an abyss from which no light escapes. But in either case, that core is no longer producing light. All the radiance of the supernova comes from the explosion's aftermath, from radioactive isotopes created in the blast decaying and heating the debris, and from the shock heating the star's outer layers as they expand. The dying star's final scream echoes across the electromagnetic spectrum. First comes a burst of neutrinos, an invisible herald racing ahead of the light. Then, the light arrives, rapidly growing to a peak brightness that can rival an entire galaxy's output of stars. For weeks, too.
Months, the debris of the star glows intensely, powered by the decay of unstable isotopes forged in the fireball. We imagine watching from a safe distance as the shattered star's remains expand in a great spherical shell, cooling and dimming over time. Where once there was a mighty star, now there is a cloud of glowing ash, the embryonic form of a supernova remnant, and, hidden at the center, a compact new child of the cosmos born from the core's collapse. This is a core collapse supernova, the fate of massive stars. It is nature's grandest light show, a release of energy so colossal that for a short time, a single star's death outshines all the billions of stars in its galaxy. But not all supernovae follow this script. There is another type of stellar death, one that begins not with a massive living star, but with the quiet ember of a star that died long ago. Before exploring the remnants and outcomes of core collapse explosions further, we will take a detour to understand the other path to a supernova, the path of the white dwarf and the thermonuclear runaway. Two paths to destruction, Type 1 versus Type 2.
Not all stars that go supernova do so in the same way. As astronomers studied the light from these stellar explosions, they found telltale differences. Some supernovae show signatures of hydrogen in their exploded debris. Others have no hydrogen lines at all. This was the first clue that there are two distinct paths to stellar oblivion. In the astronomical naming convention, those with hydrogen are called Type 2 supernovae, and those without are Type 1. We now understand that behind these spectral differences lie very different stories. The Type 2 supernova is the scenario we have just witnessed, the core collapse of a massive star that still had its hydrogen envelope at the time of explosion. The ejected material in a Type 2 supernova's spectrum reveals abundant hydrogen because the star was a red supergiant until the moment it died. These are the deaths of solitary massive stars, tearing themselves apart from the inside out. But what of the Type 1, the ones that mysteriously lack hydrogen? It turns out some stars die by borrowing a kind of second life, and then blowing themselves to pieces in a thermonuclear fury. Imagine a star, much like our Sun. After living out its life and quietly shedding its outer layers, it ends as a white dwarf, a small, dense stellar corpse composed mostly of carbon and oxygen, with no ongoing fusion. Normally, a white dwarf simply cools over the eons, but if this white dwarf has a close companion star, fate may have a more explosive plan. Picture a binary star system where one star is a white dwarf and the other is a living star. The white dwarf, though dead in the sense of fusion, still exerts strong gravity. It begins siphoning gas from its companion, pulling hydrogen and helium off the neighboring star's outer layers. The stolen gas accumulates on the white dwarf's surface, compressing and heating. For a while, this theft goes unnoticed on a cosmic scale. The white dwarf grows more massive, creeping toward a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. This is the maximum mass that a white dwarf, supported only by the quantum pressure of electrons, can hold without collapsing. When the white dwarf approaches this threshold, something incredible happens. The pressure and temperature at its center become high enough to ignite carbon fusion in a runaway manner. Unlike a normal star, the white dwarf has no way to regulate this burning. It is essentially a giant bomb waiting for a spark. The carbon fusion spreads rapidly in a wave through the dwarf's interior, unleashing a titanic thermonuclear explosion. In a fraction of a second, the entire white dwarf is obliterated in one of the most brilliant fireworks the universe has to offer, a Type Ia supernova. This Type Ia supernova is fundamentally different from the core, collapse Type 2. It is not a star's core imploding under gravity. It is a prompt detonation, a nuclear bomb on a stellar scale. The white dwarf is entirely destroyed. No neutron star or black hole is left behind.
only an expanding cloud of debris. Because the explosion comes from the sudden fusion of about a sun's mass of carbon and oxygen, it tends to produce a very consistent brightness each time. In fact, Type Ia supernovae act as standard candles for astronomers. Since they all reach roughly the same peak luminosity, we can gauge their distances by how bright they appear. We'll revisit this idea later when we see how such supernovae helped map the universe. For now, consider what the lack of hydrogen in the Type I spectrum means. A white dwarf has no hydrogen envelope. It lost all that long ago when its progenitor star shed its outer layers. So when it explodes, the debris shows no hydrogen lines. That's how we know a supernova was likely a Type Ia. Its light is missing hydrogen and often shows a distinctive signature of iron and nickel from the burned outcore of the white dwarf. There are also other subclasses of Type I. For instance, Type Ib and Type Ic supernovae are actually massive star explosions like Type II, but ones that shed their outer hydrogen before exploding. These usually happen in massive stars that blew off their envelopes via strong winds or interactions in a binary system, leaving a bare core to collapse. Thus, they are core collapse supernovae like Type II, only stripped of their outer layers, so they masquerade as Type I by lacking hydrogen in their spectra. It can sound alphabet, soup confusing, but the essence is this. One path to supernova is a single massive star collapsing under gravity. The other path is a smaller star, a white dwarf, blowing itself apart in a nuclear runaway. Both paths produce immense explosions, but their causes and outcomes differ. In one, a stellar core implodes and might leave a dense remnant. In the other, a stellar remnant detonates and leaves nothing substantial behind at its center. Understanding these two fundamental types gives us insight into the variety of cosmic fireworks we observe. Some supernovae announce the dramatic death of a lone giant. Others signal the demise of a long dead star, reignited by a companion. Together, Type I and Type II supernovae account for nearly all the stellar explosions we see lighting up distant galaxies. With this framework in mind, we can better appreciate the events and remnants we are about to explore. Now let us step out of the theoretical realm and into human history. Long before we unraveled the astrophysical mechanisms, people witnessed supernovae in the sky without knowing what they were. They saw brilliant new stars appear where none had been before, and grappled with their own interpretations. Our cosmic story now crosses paths with the human story as we look at supernovas through the eyes of those who saw them from Earth centuries ago. Supernovas in human history. Long before modern science unraveled the physics of supernovae, humans were witnessing these celestial events with naked eyes and recording their wonder and fear. To ancient sky watchers, the sudden appearance of a brilliant new star in the firmament was an astounding, often ominous event. The regular stars and planets followed known patterns, but a new star, a nova or guest star, as some called it, defied the idea of an unchanging heaven. It was as if the cosmos itself had spoken in a burst of light. One of the earliest recorded supernovae occurred in 185 AD. Chinese astronomers noted a strange guest star in the southern sky. It lingered for about 8 months before fading away, enough time for ancient observers to take careful notice. They dutifully recorded its position and its disappearance in official court chronicles. We now know that this was indeed a supernova, and modern astronomers have rediscovered the faint traces of its remnant about 8,000 light years from Earth. That ancient record, largely qualitative and couched in the language of omens, aligns with the physical evidence we see today of a Type Ia supernova explosion that occurred nearly 2 millennia ago. In late April of the year 1006 AD, a staggeringly bright guest star exploded into Earth's skies in the constellation Lupus. It ultimately reached an estimated visual magnitude of around 7.5, so bright that it was visible during the day. Observers across Eurasia marveled at it. Historical records say it cast shadows at night and was even visible during the day. The Egyptian astronomer Ali ibn Ridwan wrote that it was a large star which appeared in the south, having an enormous luster, far outshining Venus. We believe this was the brightest supernova ever observed by humanity in recorded history, what we now call SN 1006. People all over the world took note, and in some places it stirred fear or was interpreted as a portent. In North America, a possible record exists in an ancestral Puebloan pictograph, a depiction of a star next to a crescent moon on a rock wall in Chaco Canyon, which some have interpreted as a representation of this guest star. Though intriguing, such interpretations remain debated. Just a few decades after that, on July 4th, 1054 AD, all of Earth was treated to celestial fireworks as another new star appeared, this time in the constellation Taurus, the Bull. Chinese court astronomers recorded that it was initially brighter than the moon and lingered in the sky for nearly 2 years before slowly fading from view. Unbeknownst to those observers, they were watching the birth of what we today call the Crab Nebula, the expanding remains of that exploded star. SN 1054 was likely a massive star's death. The memory of this event may also have been preserved outside East Asia. Medieval Japanese and Arabic records also mention a brilliant guest star around that time. And as mentioned, some interpret the rock art in the American Southwest as depicting the event. For medieval Europe, knowledge of these events was sparse. Europe in 1006 and 1054 was in the middle of the Dark Ages and early medieval period, and scholarly astronomy was less developed than in the Islamic world or China. Moreover, Aristotelian doctrine held sway. The heavens beyond the moon were thought to be immutable and unchanging. A bright new star did not fit that worldview and might even have been ignored or explained away by those who adhered to the idea of perfect, unchanging skies. Still, by the Renaissance a few centuries later, careful observers were starting to challenge that ancient dogma. In November 1572, sky watchers in Europe, including a young Danish astronomer named Tycho Brahe, were astonished by a brilliant star in the constellation Cassiopeia, where no star had been seen before. Tycho diligently observed this novostella every night, measuring its position relative to the fixed stars. He found it showed no parallax, meaning it was far beyond the moon, out among the stars, which directly contradicted Aristotle's notion of an unchanging celestial realm. Tycho's supernova shone as bright as Venus for weeks. We now suspect SN 1572 was a Type Ia thermonuclear supernova, the kind involving a white dwarf. Modern studies of the remnant show no neutron star at the center, consistent with a Type Ia where the star was obliterated. For Tycho and his contemporaries, the event was pivotal. His observations, published in a work titled De Nova Stello, were a key piece of evidence that the heavens do change, helping pave the way for the new astronomy of Copernicus, Galileo, and Kepler. To the public and religious authorities, the new star was often seen as an omen. To Tycho, it was a scientific revelation. Only 32 years later, in October 1604, another brilliant star burst forth, this time in the constellation Ophiuchus. The famous astronomer Johannes Kepler observed it closely and wrote a book about it. SN 1604, or Kepler's supernova, became brighter than all stars and planets in the sky at its peak. Like Tycho's, it had no measurable parallax, further driving the nail into the coffin of the Aristotelian crystalline spheres theory. It was the last supernova observed in our Milky Way with the naked eye. Modern astronomers have studied Kepler's supernova remnant and, based on its characteristics, believe it too was likely a Type Ia event. Thus, the two great Renaissance supernovae were both thermonuclear explosions of white dwarfs, yet their appearance at critical moments in history had enormous impact on human thought, marking the end of an era when the cosmos was thought to be static and perfect. Throughout human history, only a handful of these new stars have been recorded, but each left an imprint on culture and science. From Chinese astrologers linking them to dynastic fortunes, to European scholars using them to question classical doctrines, supernovae have occasionally influenced the course of human thought. Most of the time, the stars live and die unseen. But when one does announce itself to us, it rarely goes unnoticed. These events also gradually built a bridge between myth and science. Each recorded observation, from 185 AD to 1572 to 1604, added a piece to the puzzle that modern astrophysicists would later assemble with telescopes and physics. Today, we can return to those historical supernovae with our scientific tools. The Crab Nebula still glows in our telescopes, and at its center, a pulsar, a rapidly spinning neutron star, blinks 30 times a second, the collapsed core left from that explosion. The remnants of Tycho's 1572 and Kepler's 1604 supernovae have been detected as expanding shockwaves in space, and careful measurements of their light, echoes, and debris composition have helped identify their type. In this way, the observations of long-ago sky watchers connect directly to the science we conduct now. The people of the past saw supernovas without understanding their true nature, but they carefully noted their appearance and timing. We, following in their footsteps, can point our instruments to those same locations centuries later to learn the why and how. It is a beautiful continuity of curiosity. Now, with the historical context in mind, let's focus on a few of those famous supernovae that have become legends in both astronomy and culture. The ones whose names have been mentioned, the mysterious guest star of 1054 that created the Crab Nebula, the brilliant new stars observed by Tycho and Kepler that altered the course of astronomy, and a much more recent stellar explosion that heralded the dawn of a new era in space observation. These are supernovas that stand out like beacons in human history's record of the sky. Witnessing great explosions, famous supernovas. Across the ages, certain supernova events stand out as especially notable, either for their brilliance, for the insights they gave us, or for the lore that surrounds them. Let us revisit a selection of these cosmic spectacles in more detail, to feel what it might have been like to witness them and to understand what they have taught us. SN 1054, the Crab Nebula's birth. It is summer in the year 1054. On a July night, people around the world gaze upward to find a startling new light in the heavens, near the starry outline of Taurus the Bull. Chinese astronomers in the Song dynasty record that it is as bright as Jupiter, eventually even brighter, visible in the daytime for weeks. They call it a guest star, and note its gradual fading over nearly 2 years. What those observers see is the death of a massive star, roughly 6,500 light years away. Today, when we point a telescope at that same spot, we see the Crab Nebula, a sprawling tapestry of filamentary gas and dust expanding in space. At its center, a tiny pulsar flashes 30 times a second like a cosmic lighthouse. This pulsar is the collapsed core of the star that exploded. The Crab Nebula, with its eerie tendrils of glowing gas, is essentially frozen fireworks from 1054, still expanding at thousands of kilometers per second. Studying it across different wavelengths has given astronomers invaluable insight into how supernova debris evolves and how neutron stars behave. One can imagine the awe of ancient sky, watchers seeing the initial explosion, not knowing that before them was the creation of a beautiful nebula that later astronomers would come to understand and marvel over. The Crab Nebula stands as a bridge between human history and astrophysics, a guest star turned enduring monument in the sky. Tycho's star of 1572. Fast forward to November 1572. Denmark. Tycho Brahe, returning from his evening walk, looks up and is astonished to see a brilliant star in the otherwise familiar pattern of Cassiopeia. A star that simply was not there the night before now shines proudly. Tycho quickly organizes systematic observations, measuring the star's position relative to the moon and known stars night after night. He finds, to his wonder and intellectual delight, that the new star exhibits no parallax, no shift against the distant star background from Earth's orbit. It must lie among the fixed stars, far beyond the moon, proving the heavens are not immutable. Tycho writes about this discovery in detail. The star shines with the brightness of Venus, then slowly fades over about 16 months. We now know SN 1572 was a Type Ia supernova, a thermonuclear explosion of a white dwarf star in a binary system. Its remnant, seen with modern telescopes, is an expanding cloud of gas with no pulsar or neutron star inside. Tycho's careful work on this supernova provided crucial evidence that the Aristotelian cosmos was flawed. It marked a paradigm shift. The universe beyond Earth was dynamic and changing. Culturally, Tycho's new star challenged theologians and philosophers. Scientifically, it propelled the likes of Kepler and Galileo to further question cosmic dogma. It is poignant that a dying star, which had likely been dead for thousands of years before its light reached Earth, helped spark the birth of modern astronomy. Kepler's supernova of 1604. Just 32 years after Tycho's event, the cosmos provided another spectacular display. In October 1604, in the constellation Ophiuchus, a new star blazed forth. It reached magnitude 2.5, outshining every star and planet in the night sky. The great mathematician and astronomer Johannes Kepler observed it extensively. People across Europe saw it. Kepler, much like Tycho, found that it showed no parallax. By this time, the Copernican view of the solar system was gaining traction, and Galileo would soon turn a telescope to the heavens. Kepler's supernova, though a brilliant apparition, was the last such to be observed in our Milky Way to date. Modern analysis of its remnant, using space telescopes, indicates it was likely a type Ia as well. Kepler compiled observations of the 1604 supernova, noting its color changes and steady decline in brightness over a year and a half. Kepler's work, published in De Stella Nova, along with Tycho's earlier nova, cemented the idea that the heavens evolve. Philosophically, it shook the last resistance to the notion that change and decay occur in the celestial realm just as on Earth. After Kepler's star, no new stars were seen in our galaxy, so these two Renaissance supernovae stand out as heralds of a new worldview. They bookend the 16th century's scientific revolution, and each bears the name of the astronomer who studied it, because their observations were so influential. Supernova 1987A, a modern spectacle. For more than 300 years after Kepler's 1604 event, no supernova bright enough to see with the naked eye was observed, though many undoubtedly occurred hidden behind interstellar dust or on the far side of the galaxy. Then, on February 24, 1987, something historic occurred. A brilliant new star was spotted in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible to the naked eye in the southern hemisphere. This was the nearest supernova since Kepler's about 168,000 light-years away. Supernova 1987A was extraordinary, not just for being visible to modern humans, but for being studied with modern scientific tools. Prior to the visible light, detectors deep underground in Japan, the US, and the Soviet Union picked up a flurry of neutrinos, 24 neutrinos in total, arriving within a 13th of a second window, just hours before the supernova was seen. These ghostly particles were emitted from the collapsing core of the star and provided direct confirmation of the core collapse mechanism we described. It was the first time humanity caught neutrinos from beyond the solar system, and they came from a dying star's core. When the light arrived, telescopes around the world and above it turned to watch SN 1987A. They saw the rise and fall of its light, measured the nuclear isotopes powering its glow, and observed its debris expanding. SN 1987A turned out to be a bit of a surprise to theorists. The star that exploded was not a red supergiant, but a blue supergiant, a hotter, more compact star. It had likely been a red supergiant earlier, but perhaps merged with a companion or shed mass in a complex way that left it blue at the time of collapse. The star left behind a striking arrangement of glowing rings, material it had ejected in earlier epochs, which the supernova's blast wave has since been colliding with, producing a fireworks show of its own as the rings brighten in response. We are still observing 1987A decades later. It's a living laboratory for supernova physics. So far, no neutron star has been definitively seen inside, leaving a tiny bit of mystery. But we detected the cobalt and titanium produced in the explosion, confirming models of how elements are forged. We witnessed the light from the blast echo off interstellar dust, giving us different perspectives of the event. In short, 1987A was like an astrophysical Rosetta Stone, offering answers to long-standing questions and posing new ones. For people around the world in 1987, especially those in places like Australia or Chile, who could see the large Magellanic Cloud in their night sky, the appearance of a new star was thrilling. Unlike in 1572, it didn't spark fear or philosophical crisis. Instead, it sparked celebration among astronomers and curiosity among the public. At observatories, champagne bottles were uncorked when the first neutrinos were confirmed and the optical counterpart was found. Humanity had waited centuries to see such an event up close, and now we finally had front row seats. SN 1987A inaugurated the era of multi-messenger astronomy, using not just light, but particles like neutrinos to study cosmic events. And it came just as computing and telescope technology allowed us to capture it in unprecedented detail. From the ancient guest star of 1054, recorded by Chinese astrologers, to the modern supernova of 1987, observed with neutrino detectors and space telescopes, our understanding has grown immensely. Each famous supernova has left an enduring legacy. The Crab Nebula's pulsar confirmed the existence of neutron stars. Tycho's and Kepler's observations helped dismantle the old cosmic order. SN 1987A gave direct confirmation of theory and a wealth of data on how supernovae work. They are shining milestones on our journey to comprehend the universe. Having witnessed what happens when stars explode, we turn now to one of the most profound consequences of these events: the creation of the very stuff that makes up planets and people. In the violent cauldrons of supernovae, elements are forged that otherwise would not exist. This is the story of nucleosynthesis, the cosmic alchemy carried out in stellar life and death. Stardust and elements, nucleosynthesis in supernovae. Every atom in our bodies has a story that stretches back to the stars. The golden ring on a finger, the calcium in our bones, the iron in our blood, all were forged in cosmic furnaces and explosive crucibles. Supernovae are not merely spectacular light shows, they are also the universe's great alchemists. To understand how, we must look at what happens deep inside stars and during those final explosive moments of their deaths. Throughout a massive star's life, its core is a fusion factory, sequentially forging heavier elements out of lighter ones. Hydrogen fuses into helium in the star's youth. Later, helium burns into carbon and oxygen. Then, in truly massive stars, oxygen, neon, magnesium, silicon, sulfur, and more in turn undergo fusion as the star approaches old age. This sequence of fusion reactions builds up the periodic table within the star, but it stops at iron. As we saw, once iron accumulates in the core, no further fusion can release energy. Without energy output to support it, The iron core succumbs to gravity and collapses, triggering a core collapse supernova. When a supernova explosion occurs, it not only liberates these pre-made elements by blowing the star apart, it also creates new ones in the heat of the blast. Consider the core collapse supernova of a massive star. As the shockwave rips through the star's layers, the extreme heat and flood of neutrons trigger a flurry of nuclear reactions in the surrounding material. In mere seconds, elements heavier than iron are synthesized via rapid neutron capture (E), a process called the R process. The collapsing core unleashes an enormous number of neutrons, and atoms riding the shockwave absorb these neutrons in rapid fire succession. These neutron-heavy nuclei then undergo radioactive decay into stable elements. In this way, elements like iodine, gold, platinum, uranium, roughly half of all elements heavier than iron, are created in the cauldron of a single supernova explosion. Meanwhile, in a Type Ia supernova, a different kind of nucleosynthesis occurs, the furious burning of carbon and oxygen into a range of intermediate mass elements, particularly a lot of nickel and iron. Type Ia supernovae are prolific producers of iron group elements. In fact, the iron that makes our blood red and the nickel and cobalt in steel are spread through galaxies largely by Type Ia supernovae. Without those explosions, iron, the heaviest element that normal stellar fusion can produce in quantity, would remain locked in stellar cores or white dwarfs. Supernovae act as cosmic salt shakers, scattering these elements into the galactic soup. Think of a supernova as a cosmic seed, spreader. The heavy elements created over the star's life, and in its explosive death, are hurled into space at thousands of kilometers per second. In the aftermath, what was once the star's core might be a neutron star or black hole, but all its outer material, now enriched with a bouquet of heavy elements, mixes into the wider interstellar medium. Over millions of years, that gas will drift, cool, and mingle with other gas clouds. When new stars eventually form from those clouds, they inherit that enrichment. Planets condense from the leftover dust and gas around those new stars, and in some of those planets, life might one day arise, incorporating the atoms that were forged in a star long ago. To put it poetically, supernovae are the universe's way of taking matter cooked in one star's kitchen and delivering it as raw material for new worlds. In the early universe, before any stars had lived and died, there were only the lightest elements, hydrogen, helium, and trace amounts of lithium. The very first generations of stars were born from this pristine gas. Many of those first stars likely died in powerful supernovae that enriched their surroundings with the first heavy elements. Each subsequent generation of stars thus had more metals available. Our Sun was born from a cloud already seeded by countless prior supernovae. That's why Earth has an iron core and rich chemistry, and why life here can have elements like carbon, nitrogen, phosphorus, and so on. All those elements were gifts from stars that died before the Sun was born. Carl Sagan famously said, "We are made of star stuff." And this is not just metaphor, but scientific truth. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in the apple pie we might eat. These atoms were forged in stellar interiors and in the titanic explosions of supernova. We carry within us the ashes of long dead stars. Every time you hold a piece of gold jewelry or take a breath of air, you are touching remnants of a supernova's fury. In a very real sense, supernovae are our ancestors. They sculpted the elemental abundances of our galaxy. They made possible the chemistry that begot life. Realizing this connection can change the way we see a starry night. The sky is no longer just a beautiful backdrop. It's our ancestral home. We have stardust in our veins. Supernovae ensure that the universe is chemically rich and ever changing. rather than static and composed of only the simplest elements. A universe without supernovae would be a dull place. No rocky planets, no breath of air, likely no life. Having explored how supernovae forge the ingredients of planets and people, let us now examine what becomes of the stars themselves after the blast. What of the core that collapsed, that neutron, rich ball that was left behind? It may become one of the strangest objects in the universe. Let's meet the exotic corpses of massive stars, the neutron stars and black holes that emerge from the wreckage of supernovae. The corpses of stars, neutron stars, and black holes. After the immense explosion of a supernova fades, after the debris is cast into space, something often remains at the center, an ultra-dense stellar corpse, the condensed memory of the star that was. In the case of a core collapsed supernova, the core's collapse is halted by forces of quantum physics, leaving behind either a neutron star or, if the star was hefty enough, a black hole. These remnants are as fascinating as the explosions themselves, for they are among the strangest objects in the universe. Neutron stars, the spinning cinders. Imagine compressing the Sun, 333,000 Earth masses, into a sphere about 20 kilometers across, roughly the size of a city. The crush of gravity is so extreme that atoms cannot survive. Electrons have been rammed into protons to form neutrons, and matter as we know it is essentially transformed into a giant atomic nucleus. This is a neutron star. A sugar cube-sized amount of neutron star material would outweigh a mountain. The gravity at its surface is so strong that if you dropped a marshmallow from 1 meter above a neutron star, by the time it hit the surface, it would strike with the energy of an atomic bomb. These mind-bending facts belie the humble name, neutron star, but they are the reality of what a massive star's core becomes after a successful supernova explosion. Neutron stars often reveal themselves as pulsars, objects that emit beams of electromagnetic radiation that sweep around as the star rotates, like beams from a lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell. At first it was so regular that it was jokingly nicknamed LGM-1, hinting at the intrigue it caused. We now know pulsars are rapidly spinning neutron stars with intense magnetic fields, whipping around perhaps dozens or hundreds of times per second. The Crab Nebula's heart, for instance, is the Crab pulsar, spinning about 30 times a second, a lighthouse flashing in the wreckage of the 1054 supernova. Every pulse we receive is a rotation of that tiny neutron star, which carries on the legacy of the once mighty star by flashing its cosmic heartbeat centuries after the star's explosive death. Some neutron stars are even more extreme, magnetars, with magnetic fields 1,000 times stronger than a typical pulsar, capable of emitting flares that can disrupt Earth's ionosphere from tens of thousands of light years away. These bizarre objects are variations on the theme of neutron stars, matter in its most compact, stable form, holding perhaps up to 2 or 3 solar masses in that ultra-dense sphere. They gradually cool and slow down over time, but for many millions of years, they can spin rapidly and power energetic emissions, effectively signaling their presence to the cosmos. In a very real way, a neutron star is the remaining core of a star, still there after the supernova, not shining by fusion, but often emitting energy as it slows down, the stellar core's ghost, left haunting the site of the explosion. Black holes, the silent tombs. If the collapsed core of a star exceeds a certain mass, not even the pressure of neutrons can halt the collapse. In that case, gravity wins absolutely, and the core continues to shrink beyond the neutron star stage. It effectively vanishes from view, leaving behind a gravitational well so deep that not even light can climb out. A black hole is born. What remains is an object perhaps only a few kilometers wide, but containing more mass than our Sun. An object with no surface, only a point of no return, called an event horizon. Inside that boundary, space, time is curved into a pit from which nothing that falls in can escape. The core of the star has become a literal hole in the fabric of reality. Black holes were once theoretical curiosities, sprung from Einstein's general relativity equations, and considered by some to be too absurd to be real. Today, we have overwhelming evidence of their existence. Many stellar black holes announce themselves indirectly, often by interacting with a companion star. Gas from the companion may spiral into the black hole, heating up and emitting powerful X-rays before it vanishes across the event horizon. Cygnus X1, an X-ray source discovered in the 1960s, was the first strong black hole candidate. It likely formed from a massive star's collapse. Now we know many such X-ray binaries harbor black holes. Additionally, the ripples of gravitational waves detected in the past few years by observatories like LIGO and Virgo have come from mergers of stellar mass black holes, offering yet another confirmation that these dark remnants are out there. To stand on the surface of a neutron star or near a black hole's horizon is to confront the ultimate victory of gravity. Time itself behaves oddly in these realms. A clock on a neutron star's surface would tick significantly slower relative to one far away due to gravitational time dilation. Near a black hole, that effect becomes even more extreme. Time essentially stops at the horizon from an outside perspective. These effects, though counterintuitive, have been measured in weaker gravity regimes and match our theoretical predictions. In simpler terms, a neutron star or black hole is the outcome of a star's final battle with gravity. The star's core, unable to hold itself up, imploded and then found a new equilibrium as one of these exotic objects. They are the cinders or tombstones left after the brilliant supernova fire has gone out. Yet they are far from inert lumps. Neutron stars can light up their surroundings with beams of radiation or intense magnetic fields, and black holes, when fed by infalling gas, can become the engines for powerful X-ray sources or micro-quasars. Even in death, these stellar remnants can profoundly affect their environment. When we gaze into the night with radio telescopes or X-ray eyes, we occasionally hear the ticking of pulsars or see the flickering high energy glow of accreting black holes. Each is a supernova after story, the quiet, persistent end, note to a star's life. In the grand narrative, a massive star lives, explodes, and then either as a neutron star or black hole remains as a kind of monument. It's humbling to realize that the universe is littered with these tiny, dark remnants, hidden endpoints of countless stellar lives. We have now followed the star from cradle to grave, born in a cloud, shining steadily, dying in an explosion, and leaving behind a strange new object. Let us cast our eyes outward again to the expanding remnants of those explosions and see what becomes of the scattered star stuff itself. Supernovae do not merely vanish, they leave behind remnants that continue to glow and evolve, creating some of the most beautiful and intriguing sights in the cosmos. Ghostly echoes, supernova remnants. Long after the blinding flash of a supernova has faded from the sky, an ethereal apparition remains, the supernova remnant. These are vast, expanding clouds of debris, the scattered ashes of a star, still glowing from the energy of the explosion and the radioactive elements within. Supernova remnants are like cosmic smoke rings, beautiful, complex, and evolving over time, marking the spot where a star met its end. If we could watch a supernova remnant in fast forward, we'd see an almost spherical shockwave racing outward, plowing into the surrounding interstellar gas. Behind the shock front trails the tattered debris of the star, a mix of elements and newly formed radioactive isotopes, forming intricate structures as it interacts with itself and the environment.
Immediately after the supernova, this cloud is extremely hot and shines brightly in X-rays. Over centuries and millennia, it expands and cools, beginning to radiate at optical wavelengths as well, and later in radio waves. Filamentary shapes appear, tangled ropes and sheets of gas shaped by magnetic fields and variations in density. One of the most famous remnants, the Crab Nebula, is a sight to behold even in a small telescope, a faint oval patch of light with subtle filament patterns. Long exposure photographs and modern space telescopes reveal those filaments in exquisite detail. Tendrils of glowing red, orange, where cooler gases like hydrogen and nitrogen emit visible light, interlaced with a bluish haze of electrons spiraling in the pulsar's magnetic field. The Crab Nebula is effectively powered from within by its pulsar. The neutron star's rotational energy keeps pumping out particles and fields that energize the nebula, making it shine far longer than it would from the explosion's initial heat alone. It's as if the remnant is a living organism with a beating heart that refuses to let the glow die out. Another remarkable remnant is Cassiopeia A. Although its originating supernova, around 1680, was not widely observed, Cass A is a young remnant about 350 years old, and high-resolution images show an asymmetric, lumpy shell of gas about 10 light-years across. It's rushing outward at thousands of kilometers per second. By studying Cass A, scientists have gleaned insights into how the supernova explosion might have been irregular, not a perfectly symmetric blast, but one that ejected knots of material in some directions more than others. Cass A's debris is rich with elements like oxygen, sulfur, and silicon, clearly marking it as the remains of a massive star. In the center lies a faint neutron star, cooling in quiet isolation. The ghost of the star is not at rest. It's expanding and colliding with its surroundings, sending out shockwaves that heat the interstellar medium and even accelerate cosmic rays that zip through our galaxy and occasionally reach Earth. Supernova remnants can be breathtakingly beautiful. The Veil Nebula in Cygnus, for example, is the remnant of a supernova roughly 8,000 years ago. It now spans about 3 degrees of the sky as a wispy lacework of ionized gas. Through a telescope, parts of it appear as delicate filaments, so thin and gossamer that one can scarcely imagine the violent event that created them. These filaments are shock fronts seen edge-on, where the shell of the remnant is plowing into interstellar space and causing the gas to glow. What was once a catastrophic blast has, over millennia, become a faint, ghostly veil decorating the sky. Beyond their beauty, supernova remnants are profoundly important to the ecosystem of the galaxy. As the remnant expands, it sweeps up and stirs the interstellar medium, mixing the new heavy elements from the explosion into the cosmic clouds. This enriched material will one day become part of new stars and planets. The shockwaves can trigger the collapse of nearby gas clouds, perhaps inducing new stars to form, so one star's death can sow the seeds for the birth of others. At the same time, remnants inject energy into the galaxy's gas, heating it and driving turbulent motions that can inhibit immediate star formation elsewhere. This feedback helps regulate how galaxies evolve, preventing them from turning all their gas into stars at once. Over tens of thousands of years, a supernova remnant will gradually dissipate. Its shock slows to the speed of sound in the surrounding medium and eventually merges with the general interstellar environment. By then, the heavy elements are well blended into the galactic reservoir. Only faint traces might remain, perhaps slightly higher concentrations of certain elements in that region of space, or cosmic ray particles that were accelerated by the remnant's shock still wandering the galaxy. Thus, a supernova remnant is the intermediate chapter of the story between the violent death and the eventual recycling of the star's substance into new cosmic structures. It's the long, fading echo of the supernova's shout. By reading the glowing wisps and shock fronts, scientists can decode details of the explosion: how fast the material is moving, what it's made of, and how it's interacting with its surroundings. Even long after a star has died, its remnant continues to tell its story. In every supernova remnant, we see a snapshot of change in action. They are elegant reminders that even after catastrophic destruction, there is quiet creation and transformation. The scattered atoms will someday cool and perhaps gather again in dark nebulae, ready to form the next generation of stars. In that way, a ghostly remnant is not an end, but a bridge to new beginnings. Stepping back from individual remnants, we consider the grand scale once more. Supernovae, whether near or far, serve as brilliant beacons in the cosmos. Their light and energy travel across vast distances, sometimes allowing us to measure and understand the universe itself. In the next section, we'll explore how these stellar catastrophes become cosmic lighthouses and what they have revealed about the space between the galaxies and the fate of the universe at large. Cosmic beacons, light across the universe. Supernovae are not only agents of cosmic recycling, they also serve as signposts on the grandest scales. When a star explodes, it becomes, for a few weeks, one of the most luminous objects in the universe. A single supernova can outshine an entire galaxy of billions of stars. This extraordinary brilliance means that supernovae can be seen across immense distances, allowing astronomers to use them as cosmic beacons or lighthouses. By observing supernovae in remote galaxies, we can measure those galaxies' distances and probe the expansion of the universe itself. Among all supernovae, the type Ia have proven especially valuable in this regard. Because a type Ia results from a white dwarf reaching a critical mass and undergoing a thermonuclear explosion, the amount of energy released is fairly uniform from one event to another. In more practical terms, most type Ia supernovae reach about the same peak absolute luminosity, like bulbs of nearly the same wattage. If we observe a type Ia in a distant galaxy and measure how bright it appears, we can compare that to the known true brightness and deduce its distance. A classic use of the inverse, square law of light. This is why type Ia supernovae are termed standard candles. In the late 20th century, astronomers began using these standard candles to chart the universe. They painstakingly observed type Ia supernovae in faraway galaxies, billions of light years distant. By doing so, they aimed to measure how fast the universe was expanding at different times in the past. The expectation was that the expansion should be slowing over time as gravity tugged on galaxies. But the supernova beacons told a different story. In 1998, two independent teams analyzing distant type Ia supernovae made a shocking discovery. Those supernovae were dimmer than expected in a decelerating universe. The simplest explanation was that the expansion of the universe has been speeding up, an acceleration driven by some mysterious force or energy inherent to space itself, later dubbed dark energy. It was a revelation that earned the 2011 Nobel Prize in Physics for the team leaders. Think about that. By observing the dying flashes of stars in galaxies halfway across the observable universe, we gleaned insight into the fundamental behavior of the cosmos on the larger scale. Each supernova that appeared in those distant galaxies, tiny dots of light on telescope images, carried within it the information needed to trace the history of cosmic expansion. The lives and deaths of stars, recorded as brief flickers in the night, became evidence for a new ingredient of the universe that now appears to dominate its fate. Supernovae also help us measure distances closer to home and map the three-dimensional structure of the universe. Even before the discovery of cosmic acceleration, astronomers used type Ia supernovae to refine the Hubble constant. By comparing distances from supernovae with the redshifts of their host galaxies, they calibrated the relationship between redshift and distance. This led to a better handle on the size and age of the universe. To this day, monitoring supernovae in distant galaxies remains crucial for improving our understanding of the universe's expansion history
and for probing the nature of dark energy. Apart from cosmology, supernovae act as beacons that illuminate their local environment. As their light travels through space, it can be absorbed or re-emitted by any intervening gas or dust. By studying the spectrum of a supernova, we can detect absorption lines from elements in the host galaxy or in between galaxies. In one famous case, light from a distant supernova passed through the vicinity of a foreground galaxy cluster and was gravitationally lensed, producing multiple images of the supernova that reached Earth at different times. Astronomers observed one image of that supernova and, by understanding the lensing delay, successfully predicted when the second image would appear a couple of years later, and they saw it right on schedule. This kind of phenomenon turns supernovae into probes of the distribution of matter in the lensing clusters. Even without such exotic effects, every supernova in a distant galaxy provides clues about that galaxy, its composition, its star formation, history. When a massive star explodes in, say, a galaxy tens of millions of light years away, we detect it and thus learn that this galaxy is actively forming stars. Supernova surveys have catalogued thousands of supernovae in all types of galaxies, revealing patterns. For instance, Type 2 and Type IB C supernovae occur only in galaxies with ongoing star formation. You won't find a massive star supernova in a quiescent elliptical galaxy, because such galaxies no longer have massive young stars. On the other hand, Type Ia supernovae occur in both star-forming galaxies and old elliptical galaxies, since every galaxy has some population of binary white dwarfs or old stars that can produce them. The sheer number of supernovae now catalogued has allowed us to identify rare subclasses and see subtle differences. We found peculiar types often by catching them in other galaxies. No two supernovae are exactly alike. Each explosion has its quirks, but they cluster into families that we can study statistically. And all of this has been possible because the universe provides an endless supply of distant supernovae, and we've developed the technology to monitor the sky systematically. Technology is rapidly advancing this field. The Vera C. Rubin Observatory in Chile, with its legacy survey of space and time, is expected to discover on the order of 10,000 supernovae per year in the coming decade. It will effectively make a high-definition movie of the optical sky, catching transient events like supernovae on a nightly basis. We will have supernova light curves and spectra in amounts previously unimaginable, likely uncovering new oddball explosions and further refining the use of supernova as cosmic yardsticks. There's also something profoundly moving about seeing supernovae in distant galaxies. It drives home the point that the life and death of stars is a universal saga. When you see a tiny, bright dot on an image of a galaxy tens of millions of light years away, knowing it's the death throe of a star, possibly someone else's sun in that galaxy, you feel an intimate connection with a distant part of the universe. These events link us with other galaxies, not just in a physical sense, but in a narrative sense. The story of stars and supernovae is a thread that runs through the cosmos, binding our Milky Way to the remotest spiral. From the closest supernova observed with the naked eye in centuries to the farthest detected by our most sensitive telescopes, each is a flash of enlightenment across space and time. Through them, the universe has communicated its nature to us. They have been beacons not only of light, but of knowledge, guiding us to understand cosmic distances, the expansion of space, and the history of galaxies. We have now covered supernovae from the tiny scale of atomic nuclei in a collapsing core to the vast scale of the accelerating universe. It seems fitting, as we near the end of our journey, to reflect on what it all means, how the death of stars is connected to the existence of life, and what philosophical insights we can glean from the cycle of stellar death and rebirth.
Danger in the sky, the threat of supernovas.
Supernovae captivate us with their brilliance and enrich us with their stardust, but they also remind us that the cosmos can be dangerous. A star's death is not only a spectacle, It unleashes a storm of radiation and high-energy particles that can have profound effects on its surroundings. If such an explosion happened close enough to Earth, the consequences could be severe for our planet's biosphere. Have supernovae ever affected life on Earth? Could they in the future? These questions take us from cosmic wonder to an edge of concern. Fortunately, the odds of a supernova occurring very near Earth in our lifetimes are low. Our Sun is not massive enough to explode, and among the nearest stars, none within the critical distance are likely to go supernova soon. The general consensus is that a supernova closer than about 25 to 50 light years could pose a serious threat, primarily by bathing Earth in intense high-energy radiation and a barrage of cosmic rays. The immediate effect of such radiation on Earth's atmosphere would be to erode the ozone layer that shields us from the sun's ultraviolet rays. With the ozone layer damaged, harmful solar UV would flood the surface, potentially causing mass die-offs, especially in marine ecosystems where plankton, the base of the food chain, are vulnerable to UV. Scientists have searched for fingerprints of past supernova effects on Earth. One intriguing find lies in ancient seabed deposits. An excess of the radioactive isotope iron in sediment layers dated around 2,003 million years old. Iron, 60, is produced in supernovae and has a half-life of 2.6 million years, so finding it on Earth's surface implies a relatively recent nearby supernova. Indeed, some studies suggest that one or more supernovae occurred about 2.5 million years ago at 150 light-years away, possibly affecting Earth's climate or contributing to minor extinctions. Another study links increased radiation levels to a minor extinction at the end of the Pliocene epoch, speculating a supernova as a cause. While these connections remain under investigation, they highlight that Earth is not completely immune to astrophysical events. If a supernova happened, say, within 30 light-years, the radiation pulse could cause a mass extinction by wrecking the ozone layer and bombarding life with UV. The geological record does show some unexplained extinction events that some scientists have playfully speculated might be due to nearby gamma, ray bursts, or supernova. Which nearby stars could pose such a threat? The good news is, none of the very closest stars are of the type to explode soon. The nearest massive stars are dozens to hundreds of light years away. Betelgeuse, the red supergiant in Orion, often comes up in discussion. It's about 650 light years away. When Betelgeuse does explode, it will likely put on a spectacular show, potentially bright enough to see in daytime, but it's too distant to harm Earth aside from perhaps some subtle effects on our upper atmosphere. Candidates often mentioned include stars like Antares, or more significantly, a star system called IK Pegasi, which includes a white dwarf that could become a Type Ia supernova in the far future. However, by the time IK Peg's white dwarf accretes enough mass from its companion to explode, it will likely have drifted farther from us. Another potential danger comes from gamma, ray bursts, extremely energetic jets that can accompany certain supernova-like events, especially the collapse of an especially massive, rapidly rotating star into a black hole. If a gamma ray burst were pointed directly at Earth from a few thousand light years away, the focused beam of gamma radiation could be devastating. Even from much further than the supernova's general radiation would be dangerous. Fortunately, such GRBs are rare, and the Milky Way is big. No known GRB progenitor is close enough and aimed at us to cause concern at present. One speculative idea is that a GRB might have caused the Ordovician mass extinction 450 million years ago, but this remains unproven and perhaps unprovable. So, while the risk is never zero, it appears that at this moment in cosmic time, Earth is not in the crosshairs of any nearby supernova candidates. We can be grateful for the margins the cosmos has given us. We live bathed in the gentle radiation of a stable, middle-aged star, far from the volatile furnaces that would endanger us. Even so, the concept of supernova threats has spurred some interesting science. For instance, astronomers have surveyed the sky for traces of past supernovae and keep tabs on the massive stars within a few hundred light years. We are effectively monitoring the environment of our solar neighborhood for potential supernova weather. It's sobering to think that events light years away can influence life on a planet, but it's also part of the dynamic nature of the universe. Human civilization might someday have detectors that could provide an early warning if a nearby star's core collapses. We already have neutrino detectors that would give us a few hours' notice of a supernova. Neutrinos escape the collapsing core before the light from the explosion gets out. Thankfully, the notice will likely be for an exciting show, not a doomsday event. Supernovae, then, are a double-edged sword, creators and destroyers. They likely helped enable life by forging elements and shaping environments, but in rare cases, they might also snuff life out. The very cosmic events that made our existence possible could, under different circumstances, pose a lethal threat. For us, the bottom line is that we should continue to watch the stars, both out of scientific curiosity and for prudent awareness. The night sky is mostly peaceful, but it has its violent moments. Knowing that our planet has likely survived nearby supernovae in the past, we carry on under the stars with both awe and respect. Now that we have contemplated the dangers supernovae might pose, let's turn our attention to some of the most extreme kinds of stellar explosions known, those that push the very limits of power, and those curious cases where a star's death might not produce much visible light at all. Extraordinary explosions, superluminous and pair, instability, supernovas. Just when we might think we've seen it all, the universe surprises us with stellar explosions, even more powerful or peculiar than the standard supernovae we've discussed. In recent decades, astronomers have identified a class of supernovae so luminous that they outshine normal supernovae by 10 or even 100 times. These are the superluminous supernovae, cosmic blasts so bright we can detect some from the early universe, billions of light years away. On the other end of the spectrum of weirdness are pair instability supernovae, theorized explosions of the most massive stars that completely obliterate the star. Both types push the boundaries of how stars live and die. Superluminous supernovae. Imagine a star explosion so bright that for a time it can outshine an entire galaxy. In 2007, astronomers observed a supernova, SN 2006 July, in a relatively nearby galaxy that was over 100 times more luminous than a typical Type II supernova. It stayed bright for many months. This was one of the first confirmed superluminous supernovae, and it left astronomers both excited and puzzled. What could cause such an extraordinary outburst? Since then, many more SLSNE have been found, often in small, distant galaxies with very active star formation. These events reach absolute magnitudes of 21 or 22, meaning at peak, they can be 10 to 50 billion times the brightness of the sun. What powers such brilliance? In some cases, it may be a central engine, perhaps a newborn magnetar left by the explosion, which pumps energy into the ejector as it spins down. As the magnetar's immense rotational energy is transferred to the expanding gas, it keeps the gas hot and glowing much longer and brighter than usual. In other cases, the cause might be the collision of the supernova's ejector with a dense shell of gas around the star, a shell the star shed in a dramatic eruption before it exploded. The kinetic energy of the explosion gets converted into light in this collision, a bit like a cosmic traffic accident, producing a brilliant flare. SN 2006 GY, for example, is thought to have been such a case. A very massive star might have thrown off a large amount of mass in an eruption or series of eruptions, and then shortly after, its core collapsed and it exploded. The supernova blast wave slammed into the previously expelled gas, producing an extremely bright, long-lasting flash. These types of interactions are classified as Type II supernovae. And indeed, Some events, observed historically as supernova imposters, where a star suddenly brightened but didn't die, were likely these precursor eruptions. The prime example is Eta Carinae, which in the 1840s became one of the brightest stars in the sky for a few years without exploding. It ejected a massive bipolar nebula and survived. Eta Carinae remains with us, albeit much dimmer now, and is still a ticking time bomb for a future supernova. Its great eruption was a supernova imposter, a false alarm, one might say, hinting at the chaos within the star. Many superluminous supernovae seem to involve stars that had similarly big eruptions shortly before final collapse, essentially setting themselves up for an especially luminous demise. Pair instability supernovae, when stars obliterate themselves. Now consider the upper limit of stellar mass, say a star with 150 to 250 times the mass of our Sun, something only likely to form in pristine conditions. In such a monster star, during its late evolutionary stages, a strange thing can happen. The core becomes so hot that the energy of gamma ray photons being produced starts spontaneously converting into matter and antimatter pairs. This process robs pressure from the core. The sudden drop in pressure causes the core to contract dramatically, the pair instability. This contraction raises temperatures even further, igniting runaway fusion. If conditions are just right, this results in an explosive thermonuclear burning that unbinds the star completely. A pair instability supernova. The star is blown to smithereens. No black hole is formed, because even the core is blasted apart in the explosion. Pair instability supernovae are purely theoretical for now, though there are candidate events. They would be extremely luminous and long-lasting because the star is being burned and ejected entirely. SN 2007 Bi is an example that was proposed as a pair instability supernova. It occurred in a small, distant galaxy and was exceptionally bright and slow to fade, with indications that tens of solar masses of nickel were synthesized. If indeed it was such an explosion, it means somewhere out there, a star of around 200 solar masses lived fast and died in a unique way, completely annihilating itself. There are also pulsational pair instability scenarios, where a massive star doesn't quite blow itself up in one go. Instead, the pair production instability causes a partial collapse and eruption that throws off the star's outer layers but leaves the core intact. The star survives that pulse for a while, until it later perhaps pulses again, or eventually the core collapses to a black hole once enough mass is lost. These pulses can also produce bright transient events. The recently observed oddball IPTF-14HLs, a star that appeared to undergo multiple explosions over a few years, might be an example of a pulsational pair instability event. It baffled astronomers by acting like a supernova that just wouldn't finish dying, brightening, fading, then brightening again 5 separate times over more than 2 years. One hypothesis is that it was a star, perhaps 100 solar masses, that had a series of internal pulsations, blowing off shells of material in eruptions, but not yet destroying its core. Eventually, perhaps that star will finally undergo core collapse and explode for good. But in the meantime, we witnessed a zombie supernova. This shows how even in death, some stars can take an unusual path. Hypernovae and gamma ray bursts. While on the topic of extremes, it's worth mentioning the term hypernova, often used to describe an exceptionally energetic supernova, typically one associated with a long-duration gamma ray burst. In the 1990s, as gamma ray bursts were being localized to distant galaxies, it became clear that at least some long GRBs were linked to the deaths of very massive stars. Essentially, if a very massive star collapses and forms a black hole, and if it has enough angular momentum and magnetic fields to produce collimated jets, we get a GRB, a blast of gamma, rays shooting out along the rotation axis of the star. If Earth lies along the path of one of those jets, we see a GRB. Meanwhile, the star's remaining material still explodes in what we would call a supernova, specifically a type IC, since the star has likely shed its hydrogen and helium envelopes. These explosions can be extremely energetic because the jets deposit additional energy into the ejector. SN 1998BW, coincident with GRB 980425, was the first strong case of a GRB-related hypernova. It was unusually luminous in radio and had very high expansion velocities. Since then, a few dozen GRB supernovae have been observed, confirming that at least some of the brightest explosions come from this engine-driven mechanism. All these extraordinary explosions, superluminous supernovae, pair instability events, pulsational multi-explosion stars, and hypernovae with gamma, ray bursts, demonstrate the incredible range of fates that befall the most massive of stars. They are relatively rare, but they are crucial to testing the limits of physics. They show us what happens in stars at the upper mass limits, how the first stars might have died, and how the most extreme energies in the stellar regime are released. These explosions also stretch our vocabulary and our understanding. They have forced astronomers to expand theories, to include magnetospin, down energy in light curves, to consider matter, antimatter pair creation in stellar cores, to account for asymmetric jets ripping a star apart. They are the flamboyant outliers of the supernova family, but often in those outliers lie insights into regimes of nature we cannot replicate on Earth. On the flip side, just as some stars explode more spectacularly than expected, some massive stars may fail to explode at all, collapsing into darkness with hardly a trace. Not every stellar death results in a bright supernova. Next, we will explore these enigmatic failed supernovae, cases where a star's core collapses into a black hole and yet produces little or no visible explosion.
The ones that failed, when stars collapse without a bang.
Throughout our journey, we have assumed that when a massive star's core collapses, a titanic explosion, a supernova, inevitably follows. But nature has a more silent ending on the menu as well. Sometimes a star can die with hardly a whimper. In these cases, the core implodes, and instead of blasting the star's outer layers apart, it simply pulls them inward, swallowing the star into a newly formed black hole. These are the so-called failed supernovae. For a long time, failed supernovae were speculative. Simulations of core collapse hinted that if the conditions weren't just right, say, if the shockwave lost too much energy and couldn't be revived by neutrinos, the infalling star might never explode. The core would become a black hole, and aside from perhaps a brief cough of energy, the star would just disappear. What would that look like to an observer? Perhaps a star would brighten a little as the core started to collapse, then fade away forever. In recent years, astronomers have actually been looking for this phenomenon. How do you catch a star failing to explode? One approach is to watch many supergiant stars in nearby galaxies over time and see if any simply vanish. Remarkably, one candidate has emerged. A star in galaxy NGC 6946 was observed to brighten modestly in 2009, and then by 2015, it had vanished from optical view. It was a hefty red supergiant before it disappeared. This object, nicknamed N6946 BH1, likely underwent core collapse and formed a black hole without a successful supernova. There was a small burp of light, a sort of mini explosion or outburst, when it brightened in 2009, but no big supernova explosion followed. The star just became a memory, detectable now only as a faint infrared source. It appears we observed a failed supernova in real time, the first of its kind. One hypothesis is that the core of the star collapsed directly into a black hole, and the weak shock generated wasn't enough to eject the star's outer layers. Instead, most of the star fell into the black hole. The small amount of energy released by the core collapse created a faint transient event. Indeed, some very massive stars might shed a bit of their envelope or produce a low-energy explosion, but still end up mostly collapsing, what we call a fallback supernova or failed supernova. Why would a star fail to explode? It likely depends on mass and the detailed physics of the core collapse. It's thought that stars above roughly 17,020 solar masses might have a harder time exploding. If the core forms a black hole quickly, it can swallow infalling material so fast that the shock is smothered. Alternatively, if the star has a very large, extended envelope, the shock might stall out in that envelope without unbinding it. The evidence is mounting. We see fewer supernovae from the very most massive red supergiants than expected, perhaps because those stars quietly collapse instead. It seems quite plausible that many black holes in our galaxy formed without a bang. What would a failed supernova look like up close? Suppose we were watching a massive star in its final days. We might see it start to dim and brighten irregularly as it undergoes convulsive nuclear burning of silicon. Then, perhaps, a sudden but short-lived glow. The outer layers briefly heating as the core collapses, and maybe a weak shock travels outward. The star might expel a small fraction of its material. Neutrinos would flood out, possibly the only strong cry of the dying star. Then, the light fades. The star's surface material, which didn't get enough of a push to escape, rains back down into the black hole. To an optical telescope, the star simply vanishes. In NGC 6946, astronomers literally have before and after images. The star was there, and then it wasn't. If such a failed supernova happened in our galactic neighborhood, we might detect it not by light, but by an outpouring of neutrinos, ghostly particles released by the imploding core without a bright optical display. Future neutrino observatories could potentially catch these subtle signals of a star collapsing directly into a black hole, giving us a heads up even when the star itself disappears in darkness. Failed supernovae are a chilling reminder that not all stars go out with a glorious finale. Some simply cease to shine, leaving no glowing remnants, just an invisible gravitating mass. If massive stars can collapse quietly, there might be many dark corpses drifting in galaxies, undetected unless they interact with a companion or surrounding gas. An entire population of silent black holes could be lurking, each marking a life that ended without fanfare. Even so, such a death would not be entirely without a signal. A collapsing star still floods its core with neutrinos and rattles space-time with gravitational vibrations, even if no light escapes. Future neutrino observatories and gravitational wave detectors might pick up these subtle clues of a failed supernova, alerting us to a cosmic death that optical telescopes would miss entirely. The search for failed supernovae continues. With more years of data and more eyes on the sky, we hope to better quantify how often stars vanish without an explosion. It's an important piece of the puzzle of stellar evolution. It affects how many supernovae we count versus how many black holes we expect, and it tells us about the upper limits of how a star can die. We have journeyed now through nearly every twist and turn in the saga of stellar death, from spectacular hypernovae to silent collapses. All that remains is to step back and reflect on the grand picture one more time. Why do supernovae matter on the deepest level? What do they mean for us, living on a small planet around an ordinary star? In our final section, we consider the philosophical reflections that supernovae inspire. How, in their death, stars sow the seeds of new life, and how we, in turn, owe our existence to these cosmic catastrophes.
Epilogue. From death comes life.
We have traveled among giant stars and witnessed their demise. We have walked through cosmic time to see how each supernova, in destroying a star, contributes to the creation of something new. Now, at the end of our journey, we pause and look back at the grand tapestry we've been part of. A profound pattern emerges. In this universe, death is not simply an end, but a transformation. The death of stars is intimately linked to the birth of everything we hold dear. Consider the atoms that compose our bodies. Every breath we take, every glance we cast at the stars, we do so with atoms that were once inside of stars. Many inside stars that blew themselves apart long before the Earth existed. It took the violent sacrifice of countless stars to sprinkle the cosmos with carbon, oxygen, iron, and the rest of the periodic table. Only then could the clouds that formed our sun and Earth have the ingredients to build rocky planets and living organisms. In a very literal sense, we are the children of supernovae. Each one of us is a composite of stardust, forged in stellar hearts and scattered in stellar graves. This truth carries deep poetry. The universe has a cycle akin to the seasons. Stars are born, live gloriously, and die. From their remains, new stars take form. Out of destruction comes creation. It is a cycle that has been ongoing for billions of years, gradually enriching the cosmos and increasing its complexity. When we look at the night sky, we see the gleam of stars that will one day cease to exist. Some will quietly fade, others will end in spectacular explosions. Yet from their ruin, new worlds may one day blossom. Perhaps somewhere in our galaxy, a supernova exploding today is seeding a nebula that, in 5 billion years, will give rise to a star and planets, and perhaps life and consciousness that will look up and wonder, as we do. There is a powerful philosophical echo here, impermanence and renewal. Stars, for all their immense power and longevity compared to our lives, are not eternal. They are born from dust and gas. They return to dust and gas. But in that returning, they fertilize space for new stars. The cosmos recycles itself. Endings are not only terminations, they are also beginnings in disguise. A supernova is an ending for a star, but the beginning of a nebula, the beginning of new chemical dispersal, the potential beginning of future life cycles. We humans, existing on our small planet, owe our existence to this grand and sometimes violent cycle. Perhaps counterintuitively, we owe our lives to explosions so distant in space and time we cannot name the sources. A star had to die for you to live. And not just one star, many. The gold in your jewelry, the iodine in your thyroid, the calcium in your teeth, these probably came from different supernovae scattered across the Milky Way over the past 10 billion years. You are an amalgam of stellar legacies. Realizing this connects us intimately to the cosmos. The boundary between us and the universe blurs. The universe is within us, literally. When ancient people saw supernovae, they often imbued them with divine or mystical significance. Today, through science, we see no less magic. If anything, the magic is amplified by understanding. Knowing that a point of light is a star ripping itself apart, and that such events made the world we know possible, adds layers of meaning to that transient star in the sky. In a way, we can view supernovae as the universe's way of keeping life possible. A universe without supernovae would be static and impoverished in elements, perhaps devoid of complex chemistry and life. Supernovae inject dynamism. They ensure that the universe doesn't stagnate, that material cycles through different forms. Out of the quiet, cold hydrogen of the early cosmos, supernova helped cook up the rich, warm complexity of planets and living organisms. As we conclude our cosmic journey, let's picture one more scene. We stand on a hill under a clear night sky. Above us, the Milky Way arches, a river of starlight. We know now that scattered among those stars are supernova remnants, the ghosts of long-dead suns, and perhaps a few stars that even now, as we watch, are living out their final moments, soon to explode. We feel the gentle night breeze, we hear the quiet of Earth, but we are aware of a colossal, ongoing drama playing out in silence overhead. One of those pinpoints of light might suddenly flare bright in our lifetimes, a nearby supernova gifting us a celestial spectacle. And while we gaze in awe, perhaps a being in another star system far away might at that same moment witness our sun as just another pinpoint in their sky, not knowing that around it a species capable of reflection and gratitude has arisen.